Okay, good morning everyone and welcome to this VLSI tutorial, day 2, session 1. I hope I'm audible to everyone. Okay, so 9:30 we'll start the session now. We have two speakers with us. Before starting, some request. So today is Monday, unlike yesterday it was Sunday. So it's working day. People are working in this building, this floor, and the ground floor and other floor empty people. So please very careful before going anywhere else which is not designated area, like go only where there are people to guide you, and so that it doesn't cause any disturbance to other people working in the office. Okay. We'll start at 9:30. We'll have 3-hour session. We'll take a break of around 11 o'clock for 15-minute break, and then we'll continue again with 11:15, and then by 1:30 will be by 12:30 will be done. Okay? So the topic for today's tutorial is the building energy efficiency into wireless IoT semiconductor devices. Okay. Some brief intro about this topic is about like all the IoT they are right. They are used everywhere in current scenario, right? For controlling, computing, and communication, right? And the main requirement for all these devices is to extend the battery life. Okay. So the focus of this paper is to how to save energy, how to make them efficient in power, save the leakage current, save the reduce dynamic current. There are a lot of method, multiple level of technique have been described in this today's session. So brief introduction about the speakers. So we have Mr. N. Venkatesh. I welcome you, sir. He's Senior Director of Engineering at Silicon Labs. He's a 35 year of industry experience. Okay. So he will be going through this session first, along with his colleague, Mr. Joseph Kalapodi. So he is Associate Engineering Manager at Silicon Lab. And he is also having around 8 years of experience in this area. Okay. So with that short intro, I will invite Mr. N. Venkatesh to start the session. Thank you.
Yep. Thank you, Radhe, for that introduction. And good morning, everyone. Welcome to this tutorial. You know, when you're coming to a conference, it usually starts with a couple of days of tutorial. So, and a long time back when I still used to learn, I used to enjoy the tutorials very much because that's how I learned a lot of concepts. You know, in 3 hours, you can learn something that it might otherwise take you 1 or 2 months to actually figure out if you want to read by yourself. So there's a lot of value to it. Every session gives you something which you can take back. You can maybe 3 important points, 3 concepts, a few ideas, and that can stay with you for a very long time. So sincerely, ask all of you to see whether what you can take away from today's tutorial. And I sincerely hope that it will be useful for you in one way or the other in your work. Right, so we are going to have a 3-hour session. We have a break, but I think you don't have to wait for the break. I'm sure the water fountain is over here. I think the coffee should also be available anytime you want to go have something instead of just waiting for that. So feel free, and feel free to ask questions at any time during the presentation. I'll try to pause so that we can get things interactive. Otherwise, it's too long to remember all the questions and come back much later. We'll do that again, of course, in the end. All right, so we're talking about energy efficiency. Now, there are many things in this particular title itself that we would like to explain. Energy efficiency. Now, everybody in the electronics domain, the semiconductor domain, has been hearing the word low power for a very long time. But we don't talk about power here. We talk about energy. Because what restricts a battery from having a long life is the energy a device consumes. So we focus on energy efficiency rather than simply low power. So that is one important difference. The second is the building into it. So as engineers who are building products, semiconductor products, electronic products, embedded systems, we are responsible for enabling the device to have a long battery life. So we have to take special efforts to build these techniques and this capability into it. So we'll talk about how we can do it. And then, of course, we are talking about semiconductor devices. It also applies beyond a semiconductor device because nobody uses a semiconductor device. They use the system in which the semiconductor device is placed. Secondly, I mean, the semiconductor device hardware itself doesn't do everything. It does a lot. A lot is done by the software or firmware that resides into it. So in the end, the user experience is what is built into the system as part of the semiconductor hardware, external hardware, the firmware, the software which is configuring it. It is all interlinked. So we will talk about everything there, even though we start with devices. And our focus is on IoT, which means that we are not talking about mobile phones, we are not talking about PCs or laptops. A lot of focus is on IoT devices, which stay asleep for a long time and suddenly wake up, send data, and so on. So a lot of techniques are focused on IoT devices. And almost all IoT devices have a wireless link. So you can always connect to the internet via Ethernet, or you can connect via a serial port to a PC, but that's the exception rather than the rule. The rule is wireless. Plenty of types of wireless. So we'll talk about all of that, and that's what the title is all about. Why are we talking about this? I mean, everybody, whenever you go to a particular session, the presenter should have some credentials. The presenter should not read about it the last week and come and talk about it. A lot of what we gain is from hard experience, from mistakes that we do, from iterative kind of design techniques that we do. So I'm talking not just because on what I have learned, but as a company, what we have learned. And Silicon Labs has the credentials. It is the world's leader in wireless connectivity for the IoT. Plenty of wireless connectivity, Bluetooth, Thread, Zigbee, Wi-Fi, proprietary, Z-Wave. So many of them are there. And our applications are in the consumer, the industrial, the home market, the medical market, the automotive market, everywhere. Everything is getting automated these days. Okay, and we are neighbors here. We have an office in the next building. So Hyderabad is one of the newest centers of Silicon Labs. It started about 2.5 years ago. And in fact, actually it has grown, and very soon it will be the second biggest in the world after our headquarters in Austin, Texas. All right, so a quick refresher on what we mean by IoT, an IoT device. If you break it down into the core components, you will have something that interacts with the outside world. A device cannot exist by itself. And there are two ways of interacting with the outside world. One way is to take data in, to see something, to analyze something. That is a sensor. Can be any types of sensor. It can sense the atmospheric situation. It can sense pressure. It can sense noise. It can take visual images. All of those are sensors, cameras inclusive. Then you have something that impacts the outside world. That is an output device, and that's called an actuator. It can be a switch that turns on the light. It can be a motor that turns on and opens the water. It can be a alarm system which sends out messages saying that please clear the room. We have an emergency. Anything that gives data out back into the world is an actuator. Both today are controlled, configured, and interacted with by microcontrollers. A long time back, a lot of sensors and systems, electronic systems, were directly handled in hardware. So when somebody walks by, a door would open, like we have in all these IR-based door openers today. A long time back, there were no microcontrollers involved. People used to have hardware circuits. They were called control systems. And when we studied, we spent a lot of time learning about control systems and how to make it stable, how to make sure that it doesn't oscillate. Okay, people don't bother so much about it anymore because it's all, you read the data and let software on a microcontroller take care of things. As soon as possible, get into the digital world today. I mean, earlier, a lot of things were done in analog. We used to use op amps and everything. We used to have filters and all kinds of filters. We used to do research on filters. And now, as soon as possible, you bring it into the microcontroller and let us do a lot of software to iterate and do things. So a microcontroller unit is a must in any IoT device. And then we have a wireless interface. And why do we have a wireless interface? It's because if you don't have a wireless interface, you can take the microcontroller and turn the actuator on. If somebody walks in, the microcontroller can say, open the door, and the door will open. That's a local system. Sometimes, okay, you may want to have things done. For example, if the temperature is too hot, you turn on the air conditioner's compressor. It can be local. But there is a value to doing it little bit remote. For example, if there is a air conditioner and there is some other heavy duty machine, which is also in the same floor, maybe you don't want to have both of them turn on at the same time. It may overload the system. So maybe knowing that some other, say, motor is on at the moment, the intelligence can actually look at two different sensors and then try to make sure that the certain conditions are being met. So that's a connected system. If they are in the same building, you can do it internally. Often, it's not in the same building. Inputs can come to you from anywhere in the world. Okay, if you want to schedule your washing machine cycles based on when the power is lowest cost, in many countries you have, demand-based cost of power. Just like our Ola and Uber, whenever demand is more, they increase the cost. Whenever demand is less, they decrease the cost. And then clever IoT engineers get that information from the the transmission company's server. And whenever the cost is low, then they turn on the washing machine and let it run. So a lot of clever things you can do if you take data from anywhere else. So in the concept of IoT, all the data goes through a gateway and hits a server somewhere where your intelligence is running. And that intelligence takes data not only from yourself, but from many other places, which make it useful to make a more intelligent decision. Okay? Now, this being the structure of an IoT system, how do we make a device have a long battery life? Now, what are all the components here that we need to look at? Firstly, we need to look at how we can get sensing done, how we can get analytics done. Earlier, we used to call it analytics because you don't have to take a decision based on one sample, right? That may be a wrong sample. You filter, you take about 10 different readings and filter it and take it. So that was called local conditioning. But you also have an advanced version of it, which is called edge computing. Today, when you're writing algorithms, a lot of people don't know how to write the algorithms. So you're wearing a device like this, okay, a watch. The watch should tell whether somebody has fallen down or not. How do you know when somebody has fallen down? If you look at the acceleration, you can find a mathematical equation to it. Whenever somebody falls down, he senses acceleration due to gravity. That means he is falling at the rate of 9.8 meters per second square. When he hits the ground, his velocity becomes zero very, very quickly. That means it's a very strong deceleration. So he experiences acceleration of minus very high numbers, depending on how long it takes to stop. So if you know those things, maybe you can write an algorithm saying that you filter it, then this is how it is done. Then if after you do the filtering and then the curve is fitting and these conditions are met, then it means the person has fallen, send a alarm immediately to the healthcare provider, his relatives, or somebody has fallen down. But that's too much mathematics involved, too much analytics involved. Now, these days, people are too lazy to do that. In fact, they don't even know how to do it. What they do is that they put a watch and make somebody fall 100 times. They put it on a stuffed toy and throw it so many times. They collect all the data and then push the data into a machine learning algorithm. And they hope that magic will happen and the machine learning algorithm will then figure out of these 1,000 cases, 100 have fall, 100 have sit down, 100 have nothing. You give all the data, the algorithm kind of converges. I mean, it works. I mean, if it doesn't work, people wouldn't be doing it. And it makes everybody capable of creating intelligent systems simply by using all of this data. And if you want to do all that, and then finally, okay, it becomes a very complex algorithm. You start with a machine learning algorithm with so many nodes. It's huge computing. But all that computing, what people normally do is to push the data out in the server. I've got lots of gigabytes of memory. I've got everything. I have AWS with me, so it can do whatever computing I want. But then by the time it may be too late, if there's an internet connection outage, then the person may not be even able to have anything help him. So they thought, okay, let's try to do inference here. Machine learning can happen here. Once you have finalized your algorithm, let's do it in our microcontroller. Can we do edge computing? So it's no longer called analytics. People are calling it edge computing. There's a history to it. Anyway, that's not the focus of our topic. So we need to be efficient in sensing, efficient in processing sensor data, efficient in computing, and efficient in wireless connectivity. And a lot of energy is spent in transmitting data wirelessly. A lot less is spent internally, but if you want to transmit for a few tens of meters or hundreds of meters, you really need to expend good amount of energy. So we'll be looking a lot at this. A lot of this is also depending on network protocols, and the analytics and cloud computing and all that do not only to some extent impact the battery life. So although they are components of the entire system, we'll focus more on what is inside this. Okay, so when you say that we'll focus a lot on wireless connectivity, you might ask which wireless. And I have so many wireless. Everything is used today. We have LoRa, Sigfox, Zigbee, and RFID, and Wi-Fi, 5G, Wi-Fi, Bluetooth, everything. Are they all required? If the world is working on English, why learn French? Why can't we have one wireless protocol? Unfortunately, the wireless, each protocol has its place in the sun. Every particular application, whether it's short range, long range, small data, more data, what kind of network is it, star network, whether the license is paid for or free. All IoT works on license-free spectrum. License spectrum like 4G, 5G are very expensive. So once you're paying a heavy amount of money for a piece of spectrum, 1 megahertz or 10 megahertz, your entire protocol becomes bandwidth efficient. So the way the protocol is defined is different for licensed spectrum versus unlicensed spectrum. Unlicensed spectrum has free spectrum, but a lot of rules. Like you're playing cricket in the Uppal Stadium here, the whole field is yours. You can do what you want. Same, if you go to another local ground here, there'll be about 10 teams playing on the same ground. I'm sure you've all seen it. It's license free. Therefore, rules have to be different. You cannot use a hard ball. You have to use a tennis ball. You cannot put a fielder in the middle of somebody's pitch. So license-free spectrum has a lot of rules. And those rules have to be kept in mind when you want to save energy. And because of all of those rules, you cannot have one size fitting all. Just like you have cellular, whether it's using it for video or voice or anything else, everything is there. The same protocol is used, some variation there, of course. Here it's all different. Very short range like RFID, you go very close to a door, or you drive your car to the fast tag toll gate, then it opens. Short range communication. Then you have longer range communication also needed, maybe at 1 or 2 kilometers. IoT doesn't have hundreds of kilometers. You don't have satellite links. Satellite links are all licensed spectrum. So a few centimeters to a few kilometers is what the range is, and each of them gives differently. But amongst all of this, we're going to focus on Wi-Fi. And that's because of multiple reasons. Wi-Fi came as a way of extending a network from the Ethernet to the wireless world. So what they did was that just like Ethernet, everything above the physical layer, they wanted to keep identical to Ethernet. So they kept everything exactly, all the I mean, it'll have the same MAC address, it'll use IP, it'll have everything just like an Ethernet connection. And finally, at the physical layer, it'll be wireless transmission. Now, unfortunately, physical layer alone doesn't cut it. Because, when you have something called medium access, how do you access the medium? You access the medium by, in the Ethernet world, you just send it. And then you sense whether what you're sending is properly being sent or not. It's called collision detection, or CD. Okay, so you see whether anything is being transmitted, carrier sense multiple access. If you sense that there's nothing being transmitted, then you transmit, but somebody may simultaneously start transmitting. Then you see whether your data is getting corrupted. If it is getting corrupted, you resend it later. In wireless world, if you are sending, you cannot receive. When I'm talking, I can't hear because my ears are swamped with my voice. The receiver is swamped with the transmitter power. So you need to sense that something has gone wrong by a different way. And that is by seeing whether somebody is sending you an acknowledgement or not. If nobody sends you, if your recipient doesn't send you an acknowledgement, you have to send it again. So there are some variations in the data link layer. Otherwise, everything else is similar. The second thing is that Wi-Fi is defined to support IP at layer 3 and beyond. And the great thing about the IP layer is that if you are sending data, encapsulating your data in IP, and then, of course, to make it received robustly, you also have other protocol like TCP. You can use on top of that, you can use anything else like MQTT and HTTP and HTTPS and so on. But all of them, the basic underlying protocol is IP. And everything has a unique IP address to which you're sending. So whether you're sending it to somebody in the same building or somebody in another continent, the structure of this thing doesn't change. That's the magic of the internet protocol, is that once you push it to a network, as long as a router or gateway can carry it across the world, routers based on the IP address can find out where the data has to be sent, and then they make sure that it reaches the destination. When I say make sure, sometimes it fails. There's nothing like failure-free communication. You always have to account for the fact that the data has not reached the destination. So TCP comes in that way, where you have acknowledgement, TCP level, and then you retransmit. That may also fail sometime. Then the application layer should know whether something is reached or not reached. Okay, so because IP is a great way to have universal connectivity, a lot of IoT devices are going natively Wi-Fi. Okay, and the other reason why Wi-Fi is popular is that there is no building today where there is no Wi-Fi. Every single home, every single office, every single hospital, every single airport, railway station, everything has Wi-Fi. So the infrastructure is already there. It's being used for networking. It is being used for access to the internet. It's being used for doing some control and command functions. It can also be used for the IoT. So the planning has already been taken care of. And it has security. I mean, the major question people ask about IoT is that how secure is it? So this security is also evolving. It's a game people play, hackers versus the developers. You keep increasing the security standards, and then somebody else comes up with a way, computing power increases, and again, you have to change it. So right now, the security standard is WPA3 with AES-based encryption. And if you want a better level of authentication to make sure that nobody masquerades you, if you program a password into an IoT device, it's stored in its flash. If somebody comes and steals that IoT device and goes tomorrow and looks at it, he can see your password in the flash. So what are the ways of preventing it? One of the initial ways was to use enterprise security called 822.1x, where each device has a unique certificate. And that certificate, if you change it and put it in another device, it may not work because it's tied to some other hardware parameters, like the MAC address. Sometimes it's tied to some hardware signatures also. All right, so then Wi-Fi gives you up to 30 Gbps of range, Wi-Fi 7 protocol, if any of you are using it. I mean, it's not yet, fully available, but when it is available, you'll get 30 plus Gbps of range. Our data rate goes up to 500 meters, sometimes more. And modified systems can go up to several tens of kilometers. So, and it focuses on low energy compared to low power. And that's one of the things that we will talk about in depth today. Okay, so when we want to understand, let's come back one step and look at what's inside that. Yeah.
Let's focus on Wi-Fi amongst the other transport technologies. Is it also representative when you? Sorry. The question is the focus on Wi-Fi as a transport technology. Is it also representative of the fact that within the gamut of IoT technologies that we see amongst devices and various use cases and applications, we see Wi-Fi to be a leading technology because we know that for wherever there is power and there are devices, there are technologies like Bluetooth LE, which seem to be more prominent when it comes to energy efficiency and low power. So that's the question.
Correct. Okay, so there are, like I said, every protocol has its place in the sun. Bluetooth also evolved to Bluetooth low energy. We spoke about why BLE. Now, why did they make it BLE? They found that, okay, Bluetooth devices cannot really work well on point cells. So, when a wireless transmission happens, the battery type determines what's the peak current that you can consume. Wi-Fi consumes a peak current of maybe 200 milliamps. Bluetooth, original Bluetooth, consumed maybe about 40, 50 milliamps. They found that you cannot make an ultra small device with a coin cell battery unless you do something about it. So Bluetooth low energy came with a definition of a better and more efficient modulation scheme called Gaussian MSK, where you could actually have 15 milliamps of current peak, and then you could suddenly use a coin cell. So if your application has to be so small that is no more than a button, and you cannot have a power source of more than 15 milliamps, then you use BLE. Okay, like if you have a sensor on your shoe which measures your steps, it's either BLE or ANT. But BLE or ANT does not take you all the way to the internet. You need to connect it to your watch. Your watch may need to have Wi-Fi. So definitely BLE has its use cases. So, but any other use case which can use a rechargeable battery, for example, okay, a LiPo battery, even if it is so small, can still supply you 150, 200 milliamps of current, but it needs to be recharged. So depending on the application, more and more applications are getting directly and natively Wi-Fi. Okay, because BLE needs one step further. And based on the advances that are happening, more and more devices are becoming direct Wi-Fi. For example, a lot of ZigBee devices in the home, smart lighting devices, smart thermostats. Almost all smart thermostats are today directly Wi-Fi. Smart locks, for example, use ZigBee long time back. Today, almost every smart lock is Wi-Fi directly. Smart lighting was with BLE or with ZigBee and Z-Wave. Today, a lot of smart lighting is also directly Wi-Fi. So if it can afford it, it can happen. There'll still be some cases where you cannot do anything other than BLE. It will still be BLE. All right, so we have sensor data coming in, and sensors are of many types. Some sensors are low power already. Some sensors are heavy duty, like gas sensors.
Hello. Good morning.
Yeah.
Regarding the use case of Wi-Fi only, so with the increase in accessibility and affordability of the cellular technology, do you think will it in future or in decades to come will it result in like low demand of Wi-Fi, or is there a comparison, or is it completely different chain of thought? But because let's say now.
Yeah, I understand your question. You are saying that why not cellular? Because 5G is also trying to address IoT, and that is all business. So the world of business, okay, the Jio and Airtel and everybody needs their business. The Verizon and AT&T need their business. So the cellular world, the ITU world, in 5G, for example, has specifically addressed IoT. Okay, so there will always be pull and push. But as of today, Wi-Fi spectrum is free. Wi-Fi is indoors and outdoors. Cellular communication works with outdoor base stations. Although they use narrowband IoT to penetrate inside buildings, you need a local network inside a building. And you know that you cannot put a cellular repeater yourself. The spectrum is owned, it's heavily paid for. So if you find that you have some low, connectivity here, you cannot purchase a cellular repeater and put it. It's illegal. Only Airtel has to do it. Wi-Fi is free. If you feel that in your basement you have a problem, you can buy a router, repeater, and put it there yourself. Anybody can do it. So the network has a great amount of flexibility without over dependence on a particular carrier. Okay, but at the same time, the carriers are trying hard to get into the IoT market. So you'll see both. Yeah.
The cellular, you have dedicated bandwidth on the spectrum.
Yep.
Versus Wi-Fi, you are going with the CSMA.
Yep. Before that, okay, did I answer your question?
Yes, but no. So just one last. So application on the application end, if I keep the spectrum aside, let's say GSM operates on a different end, but is there something different that Wi-Fi can offer? Is also what
IP Wi-Fi gives IP connectivity, and once you have IP connectivity, you don't have to worry about anything else. Okay.
Something that cellular
is doing it. No, it's not directly IP. You're not sending IP data. It has to be translated at the base station. Okay. Yeah. And he was asking about reliability. So in the wireless world, there is no question of somebody guaranteeing to receive a packet. Doesn't matter whether it's Wi-Fi or whether it's cellular or anything. A receiver any wireless receiver makes a increasingly good guess on what could have been transmitted. Even when we hear you or somebody else, I try to do pattern matching. What comes to me, it comes mixed with noise. Noise is Gaussian, it's additive. When it says Gaussian, there will be a certain percentage of cases where the noise amplitude is so much that it will swamp the signal. You can never have a completely noise-free, error-free reception. You put mechanisms in order to make it better and better. So what are the mechanisms why Wi-Fi has? Of course, it has error correction, it has retransmission and everything. What does cellular have? They also have error correction, they also have retransmission. Their one advantage is that maybe they are dedicated for that particular time slot only for you. But that is true if that's the only base station around. If there are multiple base stations, for example, a few years back, now people have actually done better things with it. A few years back, you would see that, okay, reception on the 13th, 15th floor would be worse than reception on third floor. Because 15th floor is interfered with more than many base stations. You are in line of sight with 3 or 4 base stations, all of them interfering with you. Whereas third floor is seeing only one base station. So that you cannot avoid. And people are doing a lot to do with collaborative MIMO, a lot of do with collaborative ways in which you can share spectrum and minimize interference. But interference is a fact of life in urban areas at least. Okay, so everybody has to work towards better robustness. All right, so sensor data you need to condition in some way. You might get a few millivolts. You can't do anything with few millivolts of data. We used to do a lot of things with few millivolts of analog data a long time back. Okay, we used to take decisions on them also. Okay, today nothing can be done. Nothing can be done unless it is a digital data. And before you convert to digital, you need to condition it, because the more you eliminate at the analog level, the less is the uncorrectable noise that comes into digital level. So analog conditioning is important, a very least amplification and filtering. And then you look at digital conditioning in the MCU. Digital conditioning is to do filtering and trying to eliminate redundancies, trying to reduce the amount of data, try to take 4 samples of same sensor and see whether there is too much divergence, then don't even send that data. Okay, the things we can do. Then the MCU has to put it in IP form, put it in TCP form, then send it to the wireless processor, in this case, Wi-Fi processor, where you again do Wi-Fi framing and then do Wi-Fi transmission. Now, all of these steps take energy. And the designers of IoT systems and semiconductors must look at each of them to reduce energy consumption, and many of them can be actually interrelated. We'll look at them in depth. Yeah.
How is the microcontroller unit? Research and all they are doing for FPGA and other controllers.
Well, actually, I mean, so when you're using a microcontroller, I mean, it has a CPU, it's got memory, you can write software in it, you can create packets and so on. You can also do that in an FPGA because, you know, it's all digital logic, but it's not as flexible. You can do reprogram, or if you make a mistake, you have to redesign the FPGA and burn the bit file again, which is why, I mean, all FPGAs today have microcontrollers built in. I mean, Xilinx included. They know that some part of it, people will make iterations. So FPGAs, by the way, are not really energy efficient. But the difference between hardware and doing it in firmware is the firmware has more flexibility. Hardware can do things at a higher speed if you want to do things at a higher speed.
Sir, a clarification.
Yeah.
In some slides back, right, when we showed the focus of energy efficiency, we did not circle the MCU on the sensor side. We did it for the actuator side. But here we seem to indicate that even the MCU processing is a focus for energy efficiency. So can you please clarify that?
That's what we are going to go through. I mean, the presentation is all about looking at different aspects of this.
Okay. So we are saying both on the sensor as well as actuator, wherever not all systems may have actuators, but the MCU energy spending is significant. That
is significant, yes. Yes. All right. So when you look at the processing unit, or the MCU, I called it, which is actually an SoC or system on chip, it's got a few portions in it. We are assuming something with wireless because that's our focus of today's talk is on an IoT device with wireless connectivity. We have peripherals and interfaces, which include A to D converters, digital GPIO pins. You can have I2C interfaces, SPI interfaces. All of them are there from which you can interact with the outside world. You will have a CPU, which is the actual ARM processor or RISC-V processor or whatever it is that people want to use. It has associated memory in it. It's got a protocol processor. If you're doing wireless transmission, whether it's Bluetooth or Wi-Fi, it doesn't matter. You need to process the protocol in packetizing data, in putting some destination and source and figuring out when to transmit and when to retransmit. All of them is part of the protocol processor. Then it is converted to an analog front end before it is transmitted on RF. The analog front end is D to A in the transmitter and A to D in the receiver. And when you do D to A, then you take it to the RF front end where you have a carrier which is then multiplied with the analog data. And then you're sending out carrier at modulated carrier at 2.4, 5 gigahertz or whatever frequency that you want. A long time back, people used to do IF-based up conversion, converting to intermediate frequency and then doing it. Similarly, the receiver would convert into an intermediate frequency, 50 megahertz, 70 megahertz, 455 kilohertz. These were kind of popular IF frequencies, but today everybody does direct conversion directly from RF to baseband. So this is also important. And then you have a power management unit, which we will talk about, which actually controls power to various parts of the system. When to turn off, when to turn on. That's a critical part of low energy. Okay? Low energy means you shut off as much as you don't need at any given moment and do it as fine-grained as possible. So you have a low power system. Sometimes, okay, when everything else is shut off, something has to still run. It can be just as small as a clock or a timer, but you have a low power subsystem also. So once you are creating a semiconductor device, which is an SoC like this, and a lot of people are working on SoCs today, there are many techniques that you can use to reduce power consumption. And a lot of semiconductor engineers, VLSI engineers would already be familiar with it. There are lots of stuff. First and important, reduce gate count, reduce power. You go to a lower process geometry, you can reduce power. That means you go from 40 nanometer to 22 nanometer, you can reduce power. You can do clock scaling. You know, when CMOS came, it was magic. How can a system not draw any current and still do it? Complementary, right? So one is on, one is off. It seems like magic. You don't consume any current. It's active. It's driving something, but it's not consuming current. However, during the transition from 1 to 0 or 0 to 1, there's a small period of time in which it is, both of them are intermediate. They both conduct. Okay. And so the higher the clock frequency, the more the frequency of this instances where current is consumed. And higher clock frequency also means that you're charging and discharging capacitors more often. So reducing the clock speed to no more than what you actually need is important for conserving power. And that's called clock scaling. Then you have clock gating. Why reduce a clock speed when you can turn it off completely? So can you not gate the clock? If that logic that you have is not being used at the moment, why bother feeding a clock to it? When data itself is not changing, why are you feeding clock? Then you gate the clock. And there are a lot of techniques for doing it. It's not so easy. Then you have power islands. If a particular part of the circuit is not used at the moment, why bother even powering it? Forget about not clocking it. Can I even turn off the power? So you create power islands. Then you have power modes. You can have my SoC will work in an intermediate power node. So therefore, it can process only so much right now, but that's enough for me. Later on, I want to process things in a higher scale. So I'll go to a different power mode, which is a combination of many things. Then you have, okay, dynamic voltage scaling. Power is V square by R. The higher the voltage, the more is the power consumed. So I don't want, I want to reduce. If I can do with a smaller voltage, can I not do with it? There are pros and cons for changing voltage. We'll come to that. So voltage scaling, the use of low leakage cells, when things are idle, when a CMOS transistor is on or it's off, it's not supposed to consume any current, but there is leakage. And we'll talk about that shortly. Can you use cells which are low leakage? Then very small granularity power gating, means try to do it as, if you can turn off such a small piece also, you have the greater flexibility of turning off more of your system. Then you improve power amplifier efficiency. When you talk about wireless, the power amplifier efficiency is very important. What it means is that the more complex your modulation scheme, like you're having 64 QAM, you're having OFDM, the waveform has to be reproduced as accurately as possible, which means that the amplifier should work in a very linear area. So an amplifier works in a linear area only for a small portion of its voltage swing. The closer it goes to the VDD, the more nonlinear it becomes. So if you want to make it work only in the linear, you have to bias the signal so that it only works in that linear area. That means a lot, even though voltage is very high, you're never hitting it. So you're actually consuming a lot of unnecessary current just to keep your amplifier very linear. Class C amplifiers are very power efficient, but they are non-linear. Class A amplifiers, they're very linear, but very power inefficient. And a lot of wireless transmission tends to use Class A amplifiers, but you can still have techniques where you can improve it. Then you have dynamic performance scaling. You can change the performance, the data rate, and everything else of your system. And then every system, whenever you want to change the voltage, okay, if you change the voltage by using a linear regulator, it's no use, because the linear regulator burns the extra energy that you are trying to save by going the lower current, lower voltage. So use a DC-DC converter, put a small chopper, put a transistor-based chopper and transistor-based tank circuit, which actually converts voltage just like a switch mode power supply. You do it more efficiently. So all these techniques are there. Okay, we have to use all of these, but they're not enough.
Is there a parity we should look at?
Yes. No. So you have to make sure that you are using as much of this as possible. Okay, and then you look at other ways in which you can feed. If you have the capability of doing power islanding, for example, how do you decide which has to be off, which has to be on? That has an intelligence that you can build in. Okay, we'll talk about that. So briefly, let's digress to what leakage is in CMOS circuits. See, last year, 2022, was the 75th anniversary of the transistor. Okay, when Shockley created it, okay, we celebrated a grand anniversary last year, and transistors have changed the world. So when you have CMOS, one is on, one is off, there is no current in theory, but the transistors are getting smaller. Voltages are getting lower because, power is directly proportional to voltage, square of voltage actually. So why is a MOS transistor prevented from sending current through it? It is by biasing and applying a gate voltage. If you apply sufficient gate voltage, you shut off the gate completely. If you apply the gate little bit soft, low voltage, still something can go through. So when voltages are reducing, leakage is increasing. And you have the source and the drain, and the transistor becomes smaller. The distance is less. Some of the electrons and some of the holes flow through. The smaller the geometry, the more that can go. The less the voltage, more that can leak because you're not stopping it completely. So one of the common remedies for VLSI engineers, if you are in the synthesis area, how many of you do synthesis? Okay. So how many of you do RTL design? How many of you write embedded firmware? What more? Okay. How many of you do system design on a board? Okay. So how many of you write software for various applications? Man, there's a lot of guys here who don't do anything. Huh? All right. So I'm only curious. Okay. I mean, so what question did I miss out? Can one of you help me? Huh? Physically, okay. Who works on place and route and all the pad ordering and everything? Okay, we have little. Okay, who does everything I have mentioned? Yes. Okay, who writes specs for products? New product specs. Okay, who tries to convince customers to use products? Yeah, I mean, who decides system architecture? Okay, a little bit more. Okay, I'm not sure whether it all adds up though. Okay, anything that you can help me with, because I'm really curious to know. Huh? Verification. Okay, who decides? Okay, I mean, whether somebody has done things right or wrong. We have a few people. Okay, who does? I mean, okay, when I said design, okay, who does analog or RF design? Excellent. Yeah, I mean, we have more people in analog RF design. Yeah, very good. Okay, still okay. I mean, anything else that I missed out? I do want to know. Testing. Sure. Who does testing here? System testing. Okay. And anything else? Yeah? Who did not raise their hand so far? Yeah, tell one of you, okay, what you're doing. Undergrad students. Okay, you're all students. Okay. Okay. And I should have asked who wants to do RTL design, or who wants to introduce bugs so that testers have a job. Okay, so it's all mutually go, right? I mean, if nobody creates bugs, okay, there'll be a lot of people who without a job. It'll not happen, don't worry. Bugs. Yeah, it's always there. Okay, and software companies, okay, I mean, plan bugs and plan, I should not say this aloud, but there should be some reason for subscribing to an update, right? All right. So, so what are we doing? So you have in CMOS libraries and in physical libraries, you also have high VT cells and low VT cells. A threshold really. If you have high threshold, high VT, that means that you can have lower leakage, but because you're using a higher voltage, your power consumption is higher. Okay, I mean low VT, low power consumption, but for potentially higher leakage, you can choose what you want, depending on what you can afford at the time. You can do power gating by not even feeding power to the transistor. Low granular power islands is what I spoke about. And then you can also do 3D design. Now, yes, correct. So the VT and the supply voltages are related. Yep. So that has a cost in terms of power consumption. Okay. So if you're doing a lot of switching, then you can as well use higher voltage. I mean, if your part of the circuit is asleep for a very long time, you tend to reduce the leakage of that. So you have to make an intelligent choice. All right. So everybody, I mean, I know you all heard of 3D transistors, right? Okay. I mean, a long time back, okay, all transistors were planar. Okay, when the transistor was first invented, the first integrated circuit that was invented used kind of a 3D thing, and then an efficient way of manufacturing came in, which was purely planar, and that became more prevalent because it was easy to manufacture. But being pure planar has some disadvantages. So remember, I told you this is the gate, the source and drain on either side of it. The gate is like a physical gate, I mean, it tries to prevent electrons from flowing through by applying a bias. If the transistor geometry is so small, the gate becomes a little weak. It's not strong enough to stop current from flowing through. So they come up with an idea. What if we can make the gate stronger by attaching itself to a greater area than before? Okay. Then the gate's influence is much higher. Even though the geometry is small, the influence of the gate is much higher because it encloses this, not just has a very small area of influence. And that was called a FinFET. And it became so popular that it's all over the place. And a version of that, they call it a stacked nanosheet FinFET, where you have lots of them so that you can have the gate going all around, not even, here you have only 3 sides. You have all 4 sides. And this is all 3-dimensional manufacturing. The challenge, in theory, it's very, very obvious. In practice, it's very difficult to manufacture. Okay. And so you have even a stacked, a 3D CMOS. That means why have only one transistor? Then you have to put one more transistor like this NMOS, and that is the other PMOS thing. Why can't you have both in the same 3-dimensional? Then can shrink the geometry even further, right? That means you are not using the planar area. You are like going like a high-rise building. So when you go high-rise building, you can have a higher density. So a lot of things are going on right now, and they're calling it as ribbon FET and so on. So at the transistor level, a lot of things are happening to reduce leakage, to reduce density, and to somehow continue Moore's law, which is flattening out right now. Okay, the people are desperately trying to see how we can keep Moore's law alive. It's no longer alive, actually, by the way. It's no longer do we see, twice the number of transistors in 18 months anymore. It's become, cycles have become longer, but people are still trying. Okay, so let's come back to our SOC, where you have.
How does 3D one help in reducing power?
It reduces leakage. Because the gate is actually, the FinFET reduces leakage by strengthening the effect of the gate.
That happened in stack nanosheet FET.
In the stack nanosheet, okay, you are doing it more and more. Okay, here you are doing only 3 sides. Here you are doing all 4 sides. Yeah.
How the stacking, 3D stacking?
That is only density.
Okay.
Density. That means that more per square millimeter. Yeah. Yeah, absolutely. All these are much more, much less reliable than a plain. There's no question about it. And the entire history of semiconductors has all been about improving reliability when you are going smaller. The companies which succeeded in becoming leaders, TSMC, not because it was the cheapest or the best, it was the most reliable. Okay, the yield, when it is higher, they survive. So, and that we cannot answer. There is so much to it, to putting reliability. Yeah. Yeah.
Get current is high at a low voltage. But I think it's high at a high voltage is less.
Yeah. Whenever the threshold voltage is higher, leakage is less. Yeah, correct. So now let's look at how we can convert an SoC into a way in which we can conserve energy. Let's look at a few ways in which microcontroller chips have power modes, which actually are energy modes. Okay, so if you take a typical ARM microcontroller, you will find several energy modes here. Sometimes it is running, sometimes it is sleeping, sometimes it is in deep sleep, sometimes it is stopped, sometimes it is completely shut off. And how do we choose between these? And this achieving this is based on power islanding, is based on dynamic clock scaling, based on voltage scaling. So they decide that, okay, if you are in a particular energy mode called deep sleep, okay, you don't want high frequency peripherals, but low frequency peripherals are okay, asynchronous peripherals are okay, like somebody suddenly giving you an interrupt are okay, and the state of the IOs may be active. So different scenarios based upon what you are intending to do at that time. Remember that this state may not exist all the time. After some time, you will wake up and do some processing. So before you are getting the next sensor data, let us say you have to get sensor data every 3 seconds. So when you are getting sensor data and processing sensor data and transmitting it, certain parts of the circuit must be on. If you are just waiting for 3 seconds, you can just be in a kind of a deep sleep state where you're running some clock or something, low frequency clock. If you are in a state where you might want to be interrupted by a sensor sending you a sudden important information like somebody opening the door, okay, then whatever is needed to keep that interrupt alive, you need to enable, and the rest you can turn off. So if you take any microcontroller today, the initial way of implementing, if you're all students, you will know that you can implement a IoT project using your Arduino or Espresso for hopefully a Silicon Labs chip. Then you can write the program, it will all work. But you may never invoke any of these low energy modes. And if you don't invoke any of the low energy modes, your thing will still work perfectly. But you may not meet your battery life goals. So what I tell students is that try and design a product. Don't do a project. A project is to show something working. A product has many other aspects to it, including the ease of use, including cost, including battery life, including robustness. So if you look at all of those, and as students, you do a project which is more like a product, you will find yourself suddenly more confident about a lot more things than you were if you just wrote some software and made it work. And that includes using these energy modes, understanding at this particular time which energy mode is best for me because this is what I want to do, and putting it in your program flow. So a lot of research has gone into microcontrollers, and they have done the best they can in providing the energy modes, and it's left to the embedded firmware developer to use those energy modes the best possible way. Okay, so how do they do it?
What are the example of the asynchronous peripherals? Any asynchronous peripherals?
I told you now, I mean something that interrupts you when you open the door. Okay, you're not sampling it. Okay, you're not sampling it. You just open it, and the low to high comes. The low to high should be sensed. You don't know when it will come. You're not clocking it. You're not sampling it.
Isn't it same as a backup?
A wake up circuit, you can have many different ways of waking up. You can have a timer based wake up. You can have some other external counter based wake up. For example, you can have an external counter which gives you an interrupt. So they have, microcontrollers have different mechanisms. Okay, so as an example of, yeah.
Do you have dynamic voltage scaling implemented inside microcontroller?
Yes, it's part of the SoC. So you can have voltage scaling. It's not within the microcontroller. You have to look at an SoC version of it. And you can have peripherals which are 1.8 volts or 3.3 volts. Some of them are hidden to you. If you are running the CPU at say 25 megahertz, it may use say 1.2 volts. If you're running it at 250 megahertz, it might use 1.8 volts. You may not know.
best.
Yeah. So as a programmer, you may not know, but those will be there. And that is how you get these this as microamps per megahertz and so on area. Yeah.
Do you also use charge recycling?
Which one?
Charge recycling.
Charge decycling.
It's one circuit and then part which doesn't get used and it goes to the other circuits.
Well, I'm not aware of this exactly, but maybe they do. I mean, there are a lot of techniques out there, and everybody uses what they feel is the best. I didn't quite get what you said, but if there is a technique that can help, you can be sure somebody is using it. Yeah, if you are looking at energy harvesting, like if you are discharging a capacitor, can you use it to charge some other capacitor? Okay, quite possible. Yep. So taking it. Yep. Good concept. Yeah, I'm sure somebody is using it.
All the frequency.
Sorry, I didn't get it.
The same for high frequency and low frequency.
No. See, if you run a microcontroller at 250 megahertz, it will certainly be drawing higher current than if you're running at 25 megahertz. Because in CMOS circuits, the clock rate and the current consumption are kind of proportional.
Actually, slide it is showing that.
Sorry, I didn't quite get it, but anyway, we'll come back to it later. So anyway, one example of what is turned off when you're booting up is that when you're booting up, you're not certainly transmitting. Very obvious. So at least these you can turn off. Make sure that the MCU is on, whereas all of this is off. And this is done at the SoC level when you're designing it. So now that we know that we would like to have as much fine-grained power control as possible, how can we continue transmission? So whenever you have wireless transmission, it is like a language which people use. There is a protocol. When I talk to you or somebody talks to me in a room, wherever it is, we follow a certain protocol. Otherwise, we won't even be able to understand each other. And if somebody is taking a nap, you don't suddenly tell him an important piece of information. You first tap his shoulder, wake him up, and then tell him. So in wireless communication also, it's very, very similar. So they decided that wireless devices are wireless because they need to be portable for one reason. Okay, that's not the only reason. And if they are portable, they are most likely battery powered. If they're battery powered, most likely they would like their battery to last longer. So the protocol itself has options to enable devices to go to sleep without impacting communication much. So the Wi-Fi world has something called beacons, which are transmitted by the router or the access point. The beacons are a way of synchronizing all the devices. They can synchronize their clocks. They can get important information at the end of certain beacons called a DTIM beacon, where the access point will tell the client device that while you were asleep, a message came for you, and I'm holding it for you. And I'm raising a flag saying that I have a message for you. Then the device wakes up at the DTIM interval, finds that it has a message for itself. Then it tells the access point, yes, I'm awake. Can you send me the message? And then the router sends the message. And once the router says, I have no more data, there's a flag there, which is helpfully called more data flag. If that is 0, you can go back to sleep. Now, the protocol itself assumes that the devices which are implementing the protocol have mechanisms to handle the sleep state and the wake-up state well enough that they can take advantage of this. For example, you have to wake up at a DTIM interval. That could be a few hundred milliseconds away or even a few seconds away. And with Wi-Fi 6, you can wake up even hours later. But there's a practical problem. After sleeping for so long, how do you make sure you wake up at the right time? If you want to make sure you're waking up at the right time, your clock should be very accurate. It should not drift. Now, the more accurate you make a circuit, the higher current it consumes. It is true for everything. A 12-bit A to D consumes much more current than a 10-bit A to D. A linear amplifier consumes more current than a nonlinear amplifier. Any device that has to work better, there's a cost to pay. Nothing comes without a cost. So you have to take a good trade-off between how long you can sleep so that you can still wake up reasonably close to a beacon so that you don't miss the beacon altogether, and be able to continue this wake up and sleep mechanism that the protocol allows you. Okay? And if you have a very low accuracy clock, you might have to wake up very much in advance of a beacon so that, you make sure that you don't miss the beacon because you're not sure how much is the ppm drift of your clock. So it's all part of how well you create your low frequency clock. But the standard allows you to sleep. And if you are asleep, how do you implement it? As an SoC designer, how do you implement a sleep state? Well, that's where you have to make sure that your power management unit turns off power to everything. Now, the RAM may be on or off. I'll talk about it in a minute. But there'll be one low power subsystem which will be awake. At the very minimum, that will be the low frequency counter, maybe running off a 32 kilohertz clock, which will count the time until you have to wake up again. This low power subsystem, which is powered while everything else is powered off, may also take a interrupt from an external source. For example, we use a motion sensor. A motion sensor is a small sensor which indicates whether a device has been moved. Suppose, I move this device. That means that I want to start using this remote control. So when I pick up the remote control, I want the SoC to wake up. So you need a sensor that will sense motion. And there are multiple ways of doing it. One is using a small ball sensor, a micro miniature circuit in which there's a small metallic ball which keeps moving. The more you move it, the more it shifts between 0 and 1. If you don't move, it stays at one end of the small tube. The other is an accelerometer. The accelerometer measures the acceleration. If there's change in acceleration, you can sense that it's movement. And then that acceleration can be sensed as a piezoelectric thing, right? If you put acceleration on a piezoelectric sensor, the voltage changes. So you have a small circuit which samples voltage so often and see if it changes voltage. That means that acceleration has changed. That means there's movement. So in any case, so those are all handled by the low power subsystem based on what you want, and everything else is turned off. Now, sometimes, you don't want to turn off the RAM. You don't want to lose the data because you're connected to the router. You have the state of connection with all the keys that you have negotiated with the router, security keys and so on. Everything has to be intact. You don't want to redo all the security handshakes because that will take up energy. And if you want to store all of that, you can have RAM retention logic. So RAM retention allows you to store data in RAM at a small cost, a few tens of microamps for sure, but it can store it. And when you wake up, it will save you a certain amount of time. Now, here is where there's an important concept of energy being equal to power multiplied by time. The less time you use in a non-productive state, the more energy you save. So when you wake up and you find that your connection state is gone, you have to give your Wi-Fi password, you have to establish your secret keys, you have to do your 4-way handshake. All that takes a few milliseconds. And during that millisecond, you can neither transmit nor receive. That is dead interval. And during those few milliseconds, you are transmitting, you're receiving, everything is on unproductively. So is that better? Or can you retain the state while paying 10, 15 microamps of current in your sleep state? That's a decision the system designer has to make. Very often, the wireless SoC device, including Silicon Labs devices, let the end application developer make his choice. He knows how much time he can wake up afterwards. So he can figure out, whether it's better for him to put it in RAM retention power mode or no RAM retention power mode. He can decide dynamically based on the situation what is better. and we give all the handles. But those handles are built into the SoC. You need to do that. Yeah.
Even RAM also we can do
Hmm.
implement fine grain.
Yeah.
And the implement
Absolutely. Absolutely. So only that portion of the RAM that you want to preserve, you can preserve. You don't need to preserve the whole RAM, right? So all that you can do. All right. So I told you about energy being power multiplied by time. In the wireless world, there is one more thing called rate versus range. That means that the further you're sending a signal, the weaker the signal becomes. Just like somebody is talking from that end, I couldn't really hear him that well because his signal is weak here. And in any system, there's always noise. Even though there is no interference, nobody else is talking, every system has noise. And what is that noise? That's thermal noise. Any device that is at a certain temperature has electrons moving randomly, something called Brownian motion. So the noise power is directly proportional to temperature. Anybody remember the formula for noise power in a wireless receiver? K into T into B is bandwidth. Okay, somebody remembers. So noise power seen in a receiver is proportional to temperature, is proportional to the bandwidth. Because noise is AWGN, additive white Gaussian noise. White noise is present in all frequencies. So the more of the spectrum you allow into your receiver, the higher is the noise power. If you're interested only in 20 megahertz, you put a nice band pass filter for 20 megahertz, you can eliminate noise in all other frequencies. Right? So given that there is always noise in the receiver, and given that a signal strength reduces in apparent amplitude the further you are, it means that the signal to noise ratio at any given moment can be different based on the distance from the transmitter. Now, wireless systems, including Wi-Fi, including cellular, know that there are people who are closer to the transmitter and there are devices that may be further from the transmitter. At any given time, there could be a mix. So how do you optimally use this mix? If the people who are closer to the transmitter, who are enjoying higher SNR, can they actually send or receive a higher data rate? So how do you alter data rate? In digital communication, you do it by changing the modulation scheme. Instead of using BPSK, you can use QPSK, or 16 QAM, or 64 QAM, or 256 QAM, or 1024 QAM, or 4096 QAM, which is coming up in Wi-Fi 7. The higher is the number of data possibility in one symbol, the closer is one data to another. So you need to have very good signal to noise ratio. It's like somebody is talking to me and there is a lot of noise around. I sometimes ask them to stop, speak more slowly. Reduce the amount of information transferred per second, because then I can process it better. Exactly the same thing with wireless. Okay, for example, the Wi-Fi 11G gives the option of 54 Mbps, 36, 24, 1 Mbps. 1 Mbps uses, for example, BPSK. 54 Mbps uses 64 QAM and different levels of error correction. So if you want to use 64 QAM, you need a much higher signal to noise ratio than if you're using 1 Mbps. So the idea is that you would want to transmit data at as high a data rate as possible, because the transmission time for the same amount of data, 1.5 kilobytes of data, you can transmit in a quarter of a millisecond if you're using 54 Mbps, whereas it can take up to 12 milliseconds. And remember that your current, if your front end is on, your MCU is on, current consumption is the same. So here you're using about 12 into 4, 48 times the energy for receiving the same 1.5 kilobits per second, kilobytes packet. Right? So the faster you can finish it, the better. And what people do is that, why am I not able to use very high data rate? Because if somebody is sending me data, I'm not able to decode. I said, please tell me I'm not able to receive it. No ACK. Then the transmitter have to send again. Now the transmitter knows that you did not receive previously. Now the transmitter automatically downshifts the data rate. It's called automatic rate fallback. So if you fail to transmit at a one rate, you try again at a smaller rate. We also do that. When somebody doesn't hear what we are saying, we try speaking louder or we try speaking slower, so that now maybe he can understand it properly. So same thing the system also does. Now, if I am a little bit deaf, I will unnecessarily make you speak slower. So can a system receiver be made a higher performance receiver, so that even with a lower SNR, you can still get a better data rate? And that is where wireless systems designers spend a lot of time and effort optimizing, right? So they do lots of things. Okay, signal fails because of signal degradation. So you try to improve the receiver performance, so that even if signal to noise ratio is lower, I can receive data better. What do? They have more complex algorithms. You know that there is a space probe gone to Neptune. From there, you're sending data and you're receiving it. Millions of kilometers away, the signal here is no different from noise. Yet they get information, pictures of Jupiter. How do they do it? It's by sending the same data over and over again, thousands and thousands of bits to get one bit out. So you can aggregate information by collecting energy from as many bits as possible and using complex error correction mechanisms to process it. So you can make the receiver better. You can have more levels of precision inside to process better. Everything comes at a cost, remember. You can process more. That means you can have a Viterbi decoder which can go to greater depth. You can do lots of processing in the receiver at a cost of size of the circuit increasing, but eventually you can get gains. You can optimize for multipath. For example, wireless, and if you're in Bluetooth, normally everything is line of sight because of the distance. Whereas in Wi-Fi, very rarely do we actually see the router. It bounces off walls and furniture and people and come in. So you have to process for multipath as much as you process for noise. And multipath processing involves equalization techniques. You can have better and better equalizers, more taps into it, and you can get better at multipath handling. You can create circuits, better noise figure, use more energy, use higher voltages. You can have better error correction performance. Remember, the standard says that you have a rate 2/3 convolutional coder in the transmitter. In the receiver, how do you process that rate 2/3 convolutional coder? Your choice. It doesn't say that you have to do it this way. You can use a Viterbi algorithm with a certain amount of depth, more depth. You can do soft decision decoding. You need not do hard decision. It's up to you how much processing you want to throw at the receiver so that you can get the data out. And throwing the processing comes at a cost, and that's where your cleverness comes in. If you are a smart algorithm designer, you do things in MATLAB, you pass it on to a RTL designer, he may make it into inefficient hardware. So in most, if you want to optimize it, you have to look at what the algorithm is doing and how the algorithm is implemented in actual RTL. You have to do it all together. So all these techniques you can use. Okay. So other ways of improving wireless, which is supported by the standards, is increasing the probability of getting a packet correctly is something called link margin. Link margin is the amount of loss the link goes through. How can you improve it? You can use antenna diversity. If the transmitter doesn't worry about too much power consumption, you can use 2 antennas. Or the receiver can use two antennas. And then you can when your receiver uses two antennas, it is called combining, or MRC is maximal ratio combining. You can combine signals from two sources and average them. And you know what is the average of noise? Average of noise is 0. The more you average noise, the more you can eliminate it. The more copies of a same signal you can get, which is impacted by random noise. And when you combine it, the higher will be your signal to noise ratio. If you add two signals with noise on them, the resulting signal has twice the power and the same noise, because noise is random. They can add or subtract. So you can combine two receivers to get MRC, 3 dB gain for two antennas. STBC is something when you have multiple antennas in the transmitter. That's also there in the Wi-Fi standard. You can also improve your capacity, have higher modulation schemes. Wi-Fi is doing that. Every new generation of Wi-Fi gives you more data capacity. It not only gives you higher data rate, but also improves your power, average power consumption. You can eliminate overhead by using a large packet with a small header. And that's something called aggregation. And Wi-Fi 4 onwards, packets are aggregated in Wi-Fi. Up to before Wi-Fi 4 or 11N, aggregation wasn't there. It also improved with better coding techniques, LDPC instead of convolutional codes. Then you can use beamforming. That means you can use multiple antennas, and then you can combine the antennas with a certain phase so that the antennas point to a particular direction. You know that when you have two antennas combining the signal, in one direction, the signal of one antenna may be 180 degree out of phase with this one, because that's equivalent to the half the wavelength. So if it's 180 degree out of phase, it subtracts. So you get a null. If it is 0 degree out of phase, you add. So that's why antenna arrays have a certain directionality. And you can use beamforming with multiple antennas. You can also improve throughputs with MIMO. The MIMO is also magic. So it's so much of a revolutionary thing in wireless communication that I thought I will just explain it to you. Let's say that you are sending 3 transmitters are there, and you want to send data to a receiver. Now, obviously, if one of them is transmitting, if the others also transmit, the receiver gets garbage. So you have to do time division, multiple access, or TDM, so that one transmit, then the other one, then the other one. But what if you transmit all at the same time? They figure out that you can still receive the data properly, provided you receive as many copies of the signal as there are transmitters. So if you have antennas which are 1 and 2, they are sending different data, let's say X and Y. You are receiving them on 2 different antennas. So this X comes here, but is multiplied by some coefficient, because the channel is different. The coefficient means that the signal is altered in amplitude and phase, plus noise is added. Okay, so here you get some receiver 1 is H11X plus N1. So receiver 2 is H21X plus N2. So important thing is that this H11 should be different from H21, because the antennas are physically separated by a little bit. So the signals are not altered by the same amount, their coefficients are different. So when you have 2 variables and you have a simultaneous linear equation, okay, A is equal to AX, you get Y1 is equal to AX, or Z is equal to AX plus BY, okay, and then some other variable K is equal to DX plus EY. As long as you know the coefficients, you can solve for X and Y. So as long as the coefficients are not related. If the second coefficients are twice the first coefficient, you basically have one equation only. So simple simultaneous linear equation, if you can use, if you know these coefficients, then you can decode both of them, even though they were transmitted at the same time. So they find out the coefficient by sending a known signal first, and then with one antenna, then known signal with another antenna, then determining H11 and H21, and then actual transmission starts, then they decode it using, whenever you want to solve linear equations, one of the ways is to use a matrix. You invert the matrix and then multiply, you get the coefficients, get x and y. That's what people do. But the problem here is that there's noise. So you don't get coefficients exactly. You get coefficients altered by noise. And therefore, you cannot get a straightforward solution. You have to iteratively try to see what solution is the best fit here. So wireless reception is all about making better and better guesses. Oh, could this be the right one? Okay, this has so much error. Or maybe this is what was transmitted. Oh, this seems to have so much error. Eventually, which has a best or smallest error is chosen, and that's called maximal likelihood detection. So those things are all used. And then today with Wi-Fi 6, you also have multi-user MIMO, where one station which has sending small amounts of data, which is a IoT device with minimal amounts of data, is sending data, sending something, but the capacity of that particular channel is so high that even though you can transmit, say, 2 gigabits per second, you're using it to send only 240 bytes. But still, that overhead and everything, the time slot is gone. So what if you have multiple IoT devices? Can you share the same time? So multi-user MIMO allows the devices to be transmitting at exactly the same time. And then the receiver has the way of decoding each of them separately without getting interfered with. So that's called multi-user MIMO. That also improves efficiency, energy efficiency of IoT devices. So I already told you about how wireless LAN power save use DTIM. So the one of the problems in the IoT world is increasing density. More than hundreds of devices are there. So when there is more density, there is more contention. You as an IoT device wakes up after 300 milliseconds and decides to tell the access point, I'm awake, please send your data. Similarly, 20 other IoT devices in the room also wake up at the same time. Then they all transmit at the same time. And then all the transmissions go bad, no acts. Then each of them has a random timer to decide when to transmit again. So they end up wasting a lot of time waiting for a chance to transmit. So that was changed with Wi-Fi 6, the current generation of Wi-Fi, or 802.11ax standard, with something called target wake time, where the access point can tell each IoT device, don't wake up too early. This is the slot you have to wake up. I'm allotting it to you. You wake up now and send me your data. Okay, so the contention is reduced. It enables hundreds of devices to be coexisting in the same network without trying to simultaneously transmit and waste energy of everybody. Okay, so finally, at the having used all the SoC level techniques, hardware techniques, power scaling, performance improvement in Wi-Fi, in wireless reception, everything, you have to decide at the system level, what are you doing? How frequently should you be sending your data? How much time am I taking to wake up my wireless subsystem? How much time is it taking to prepare itself to connect to an access point and send data? And during that preparation time, how much current it's drawing? And finally, when it is transmitting, how much current it is transmitting? You need to have all of this information before you can decide how frequently you need to wake up, whether you need to be in RAM retention mode, whether you can do other modes, what's best for you, you need to decide. Okay, so there's one more small issue about Wi-Fi is that sometimes, when your neighbor is transmitting, you might think that the channel is occupied and stop transmitting. And people realize that that's a very commonly occurring problem now. They introduce something in Wi-Fi 6 called BSS coloring, where you can ignore certain transmissions, knowing that they are a little bit far away. You have enough power, so you can push through your data, and SNR will still be good enough. Okay, so there's one more thing that system designers do, like I just now told you, which is important for you, latency or battery life. If you can live with low latency, that means that you can wake up every 5 seconds. You can wake up every 5 hours. And if you are a controller which actually gives some information, if somebody decides to say that this road is now open, somebody sends the data, you're waking up after 5 seconds or after 50 seconds, and then saying that this road is open. That means there's a latency involved. Obviously, it's a battery operated devices, you're saving current, saving energy by delaying your wake up. But is there a sweet spot between sleeping longer and having lower latency? Or can you have both? So there is a new standard called 802.11ba, where you have a very low power receiver called wake up receiver, which works at a few tens of microwatts. And then you send a wake up packet before you send your actual packet. This wake up packet wakes up the receiver, and then you can send your data packet. Now, this is revolutionary. If you're having a mesh network, for example, all the intermediate nodes have to be always on because it doesn't know when it has to relay data. So what if you have a small receiver which can wake up but not decode data? And I use something called on-off keying here, where you have energy bursts coming in a certain pattern, and these are not processed at all. They are just converted into digital. Then you have ones and zeros. You have a small digital correlator. It's an autocorrelator which keeps running. It looks for a certain pattern of energy here. And if the pattern matches, it knows that wake up is going to happen, and then it wakes up the receiver. Okay, so you can do a lot of things. You can do many other things for innovation. You can intelligently change your ADC. You can reduce memory access. Every time you access memory, it takes energy, and all those things we can do. And sometimes, okay, when you get a data, and then you find that the signal to noise ratio is too small, there's no hope that you can decode it. You can forget about the packet and shut it down. Like when somebody is giving you a lecture and you miss the beginning, then I'm not going to understand it, or let me sleep. Same thing this also does. So you can use everything in your system. All right, so this is the end of part 1. In time for your chai and coffee. We looked at reducing power, you looked at saving time, you looked at how standards help us. We looked at how device developers have a lot of scope. They also have to think in a lot of ways in order to increase battery life. You can do it at the semiconductor level, at the software level, at the system level, and every part of the system impacts your energy consumption. All right, so 11:02, we are off by 2 minutes, but we can still have 1 or 2 minutes of questions before we go for chat. Yeah.
Regarding this low power backup receiver, is that a dedicated one or a broadcaster sent to all, and whoever matches that backup?
Anybody, not dedicated. There is no, it's not unicast. Everybody will wake up if it receives it, but different receivers can be tuned to different patterns. So if the transmitter wants to wake up a particular receiver, he can send that pattern which only that receiver is programmed with. Yeah.
So what is the power consumption of that?
Yeah, about 100 microwatts. Depends on how you implement it, but typical is around 100 microwatts. I mean, you can be clever and do it better. I'm just quoting a typical number.
So I have one question. Do we have any kind of process of doing this UE assistance based power saving Wi-Fi also? Kind of device can tell the AP to do certain config to share.
Yep. So I mean, for example, in networks, okay, there's something called ARP, where you're trying to do an address resolution. The device can tell the router that if somebody is trying to query my MAC address to IP address, you answer on my behalf. And as the router supports that standard, it is there in the Wi-Fi standard, then the router can itself answer for the device without passing on that query to the device. It's available. Yeah.
You showed a slide in which there were multiple subsystems, RAMs. Which block would give some more power?
Usually the wireless transmitter, because the transmitter has a power amplifier that is very inefficient, less than 20% in most wireless scenarios. So when you are transmitting, you consume the highest power. So you try to reduce the transmission time. Yeah.
There are two, this no, so much power are there. Dynamic power, leakage power. How to reduce the board?
Yeah. So dynamic power, okay, is based on the clock frequency. There's not too much you can do about it. The more transitions you have, the more energy is lost. You try to reduce it by deciding whether you really want that circuit to be clocked. Can you avoid clocking it? Can you reduce your clock rate? So all that reduces your dynamic power. Your leakage power is based on the structure of the cells and what kind of cells you want to use. Whether you can reduce leakage power by turning off a device. Instead of shutting down clock, can I just power down that circuit? You have to decide.
So you talked about there's a sweet spot between like when we want to transmit and we want to have high latency. So is it better to increase the edge computing to understand the data and transmit less, but spend more power in edge computing? And as compared to
Okay. So there is no clear answer to this. It depends upon the situation. But there are many cases. I mean, his question was, do we do edge computing or do we not do edge computing? How do you decide which is more energy efficient? So the answer is that it really depends. Sometimes your speed of response becomes more important. Then you do edge computing. Sometimes there is a data deluge. When you have lots of sensors sending lots of data, the energy spent in sending all the data to the server may be too high. Over a period of time, you can decide that if you are taking data from 20 sensors, out of 20 sensors, okay, there are some 7 sensors which send the same data, some 7 more. So they are redundant. How do you know they are redundant? You will not know initially, but over a period of time, you will know that these are redundant. So you can stop sending those data. So you can iterate. So how do you know whether redundant? That's edge computing. You have to do something to find out whether in this scenario things are different or same data is being repeated. So a lot of things which can be done through analysis.
But if you want to do edge computing, you want to have a better performance, right?
Ideally, you don't want to do, ML processing using a CPU. You want to do hardware accelerators. And there are plenty of companies today which giving hardware co-processors for ML. And that's what people ideally should use. Yeah.
Yes, Silicon Labs, you are IoT chip maker. But in a whole ecosystem of IoT, how much power will be consuming by
the chip itself? Well, okay. So his question was in the whole IoT ecosystem, how much power is consumed at the chips compared to rest? Highest power is consumed at the data centers, where all that tons of IoT data is gone and stored and processed. So the data centers today are one of the biggest power hoggers ever. If you want to establish a data center, you have to first build a power plant. Then only you have to build a data center. Devices is not cost of energy as much as the cost of the batteries that you keep doing and the convenience of not having to change battery. Okay, so you're okay. Right now, the world is okay with pushing computing and power consumption to the data centers. All right, so time for a break.
We'll take a short break.
Yeah, I'll talk to you.
You can take the question later on. We'll take a short break. The outside tea and coffee are available. So one other request is don't roam around here and there where you're not supposed to roam because it's working day to day. And we'll be back by 10 minutes, 11:20. Okay. I think we'll get started, guys. Just settle down. We have 1 hour to complete, so we'll finish by 12:30.
Check.
Okay, we'll wait 1 more minute maybe, so that people who are outside can come.
Okay.
1:30, 2:35. Okay, I think we're going to start the part 2 of it, okay, which is putting theory to practice inside an IoT chip. And Mr. Joseph from Silicon Lab will go over it now. Okay, over to you, Joseph.
Okay, we'll get started. Welcome back, everyone. So in the second session, in the first session, we have seen a lot of information related how the power can be saved in an IoT product. So in this second session, we will see how all those techniques and tools put together to achieve the low power consumption. So this will be specific about our products, where we achieved the low power. So I'll be talking about the introduction to the power modes, the modes or the domains that whatever the modes that we have, and basic power modes like low power and ultra low power modes. And we'll go through some of the customer case studies, how they have implemented the power save mechanisms in their applications to make their IoT product better and better battery life. And next, I'll quickly go through the summary of Tolly report, which is a third-party report where we got it tested with the other third-party vendors also, and how we are better in terms of battery life. So I'll go through the summary of that Tolly report, and I'll also go through a demo. It's a recorded demo. So we have seen the power domains previously, right? Venkatesh, as Venkatesh mentioned. So for any IoT product, the power consumption is the very key. If a IoT product has to succeed, it has to get or attain more battery life, or longer battery life is achieved, is expected. So if for every IoT product, if a device has to come, or if a device needs to consume less power, what are the techniques? So depending on the state of the module, the power mechanisms are implemented. So for example, in this power domains, we have low power subsystem, power management unit, we have RAM, we have CPU, we have peripherals and protocol processor, we have RF and analog front end. So these all domains can be switched off depending on the state. So for example, if the module is booting, the analog front end, RF front end, and the protocol processor, these subsystems can be shut off, and the remaining will be active. So we'll see the basic power modes of our RS916 products. The first one is the low power mode. In the low power mode, the baseband programming, the analog front end circuit, the RF circuit, these all will be powered off, and the host interface, whatever the communication between the host and the module, will be only active. So this is what the low power mode is. And in ultra low power mode, along with the all the portions of the chip will be shut off along with the host interface. So all these except the low power blocks like ULP controller and the power management unit, the remaining parts of the module will be shut off. So sure.
When you say shut off, means the voltage will shut off, or it's just a power domain and power domain?
It's power domain.
What is VLSI controller?
It's a ultra low power controller which is specific to our module. So
Some kind of a 10-0 kind of a.
it's not like that. It's our power save internal. We have one processor in the RS916 module itself.
Fixed function or some programmable?
It's like it's like upgradable. It has also the firmware versions and stuff.
When you say host interface is not it means host interface is we have to initialize.
It's not like that. So the host interface will be in sleep, and whenever we get a packet from the host, we can wake up the module. So we have basic handshake mechanisms.
Can we go back to the
Sure.
In the first one, I think low power, the Mac processor, some portion you're showing as green.
Right.
Power domain part is green.
That is the host interface part, which will be active. So in order to maintain the connection between the host and the module.
Some portion you can collapse through some switch or something.
Right. So we have different handshake mechanisms. Yeah.
When we talk about low power and ultra low power, right, what is exactly the industry specific values of the power consumption? Like which state that is giving low power?
Right. So we don't have any specific number, but theoretically it is possible. It will be in few microamps. So here in low power and ultra low power, depending on the host interfaces and depending on the states that we shut off, the low power and ultra low power is maintained. So for example, in low power mode, it will be around, in the milliamps of current. But in ultra low power, we will get in the microamps of current. So it is further reduced in the ultra low power, where we are shutting off more number of blocks. Sure.
When we talk about power modes, the values of the power modes,
right,
why we talk about the amperes of current which is being used and not about the wattage. For example, if we have the pacemaker or something, there specifically the value of the wattage, that is the 12 picowatt of that device is mentioned. So why it's oriented towards the current and not the wattage?
Well, so we can it's in the term how we use it. Like we can also tell in the order of amps, and we can also tell in the order of milliwatts, like that. So some customers or some terminal, depending on their way of thinking or delivering, they will add that particular way either in the order of amps or in the order of milliwatts. So in some of the customer cases, you can also see some customers measure the power in terms of milliamps like that. So we'll see that. So a handshake mechanism means this is a method to wake up the module. How once the module is in sleep, how we can wake up the module so that it can receive the packets from the host. So there are two methods, GPIO based and another one is the message based. So in the GPIO based, we will use two GPIOs, one for wake up request from the host and one for waking up the wake up request from the RS9116. Second one, we have a message based mechanism. This is showing not only. So we have a message based handshake mechanism in which the host and the module will exchange some messages so that there will be mutual contact or mutual agreement, so that host will send the packet and module will receive, and module whenever it wants to wake up, then it will send a message to the host. And this is something like a message based. First one is the GPIO based. It is purely based on, we will set one GPIO and we will assert and deassert. Depending on that, the communication will take place. So these are the two handshake mechanisms which we mostly use for keeping the IoT device into the power cell.
One question. Sure. So when you say message based, right?
Yeah.
If the device is sleeping, your module is sleeping,
right?
What will receive the message? Do you have another thing like a line that is first toggled and then the message is sent? How does it happen?
Right. So first, host will signal that I have some packets, and a module will say that okay, it will wake up. A module will wake up at particular intervals of time and check whether AP has the packets or not. So those things I'm going to talk about in the next few slides. So you will have a better understanding of how this can be done. Okay. So there are 5 modes in RS916 which we have implemented. Power save mode 1, power save mode 2, power save mode 3, and 8 and 9. So in power save mode 1, we are not using any handshake because that is the power save mode. Depending on the customer use cases, they can utilize these set of power modes and implement their application. For example, if they don't have any restriction on the power, then they can go for power mode 1, where there is no handshake. And power mode 2 and 3, they are basically 1, 2, 3 are given in the connected state. When the module is connected to the access point, for example, you have a mobile which is connected to the access point, in your home router, right? So during that time, these power save mode 1, 2, 3 can be used. And we have 8 and 9. These can be used whenever the module disconnects from the access point. So basically, if you are going away from the region where the access point is there, or we are going out of the vicinity of the access point, then these two power modes 8 and 9 can be used. So in power mode 2 and power mode 8, we will use the GPIO based handshake. And in power mode 3 and 9, we will use the message based handshake. So there are, as I mentioned, 5 power modes are there, and going further, classifying them in connected and unconnected sleeps. So we have different protocols. Then how we implement this power save feature or power consumption mechanisms in different protocols like Wi-Fi, Bluetooth, and BLE. So we deal mostly with Wi-Fi, Bluetooth, and BLE. So you can see the so you can see 2 states. One is the connected state. One is the connected state, and the other one is the non-connected state. So if we take wireless Wi-Fi, so this is the state where the module is connected to an access point. So we will use power save mode 1, 2, 3 in the connected state, and we will use 8 and 9 when the module is not connected to an access point. Similarly, in case of BT Class A, here the discoverable, this is the inquiry scan and the passive scan. So in the discoverable mode or the connectable mode, we will use power save mode 1, 2, 3. And in case of ideal mode, we will use 8 and 9. And same in case of BLE. When it is in ideal state, we will use power save mode 8 and 9. And when it is in the connected state, like advertising state or scan state. So in BLE, advertising state and scan state are considered as the connected state. So we will use power save mode 1, 2, and 3. So these are the typical modes with respect to the protocols, how we use them, and which will help us in consuming, which will help us in getting the low power consumption. So here we'll go through the each mode in detail and see how the software is designed so that we can achieve the low power in the IoT devices. So in the power save mode 1, only the RF part of the module is shut off, and the remaining everything will be working normally. So the module can receive data from so we have station and access point, I mean client and router. So module can receive data from the host at any point of time, but it can send only data at the DTM interval. So maybe I'll quickly go through what this DTM is, and if you understand how the DTM is designed or what the spec says about DTM, then you will understand all these power modes better. So normally in our access points, so we have access points where it will be sending the beacons at particular interval. So that is called as the beacon interval. So beacon interval typically will be 100 milliseconds. So every 100 milliseconds, access point will send its features. I mean, I am there. Like it will exhibit its feature saying that through the beacon. So in the beacon, we have this TIM bit. So TIM is the traffic indication map, and DTIM is the delivery traffic indication map. So in case of TIM, every beacon will carry out a TIM, which is a traffic indication map. I mean, when a station connects to an access point, it will get one association ID. So for an access point, there can be many clients, right? So each client will get or will be given after connection an association ID. So how does the client know that AP has some packets, right? So AP, how does the AP also know that station has some packets? So since it has different clients, how does the AP know that I have to buffer the packets for particular station? So using this association ID, AP will buffer the packets at its end. And once the module wakes up from its state and connects to an access point, when it wakes up, and it will send a PS4 to retrieve the data from the access point. So every beacon will have a TIM bit, which is a time indication map, traffic indication map. So according to the spec, we have something called information elements and information fields. So all the information fields are fixed and they are mandatory. All the information elements that are TIM and DTIM, they are optional and they are variable. So in the TIM, every beacon will have some TIM element, which is variable, and depending on that, every TIM will carry some information related to the access point. So this is only the unicast traffic between station and the access point. And DTIM will be delivery traffic indication map, so which will be for broadcast and multicast traffic. So here what will happen is, as I said, every beacon will carry TIM, but every beacon will not carry DTIM. For example, in our access point, we will have some configuration like DTIM period. So if we set the DTIM period as 3, for example, every third beacon is the DTIM beacon. So first beacon, second is TIM, second beacon will contain TIM, third beacon will contain the DTIM period, which means it has some multicast and broadcast data. So after the beacon, I mean when the beacon is the DTIM beacon, immediately after the beacon, the data will be transmitted to the clients. So keep that point in mind. So now, while coming into the power save mode 1, once the station connects to an access point, Then we have some commands to put the module into the sleep. So the module is in, let's assume that now the module is in sleep. So host can send data at any point of time, and host sends packet to the module, and the module checks if it is a DTM time or not. So I said every beacon will carry team, and every DTM period, I mean, for example, if the DTM period is 5, every 5th beacon will be the DTM beacon. So the module will check if that is uh, if that is a DTM beacon. If it is not a DTM beacon, then it will be again in the power save. And if after the module sends packets, if it is a DTM beacon, it will wait for that beacon. So if it is a DTM beacon, immediately after DTM beacon, data will be transmitted, right? So the station will wake up to the nearest beacon and receives the data. So here it will wait for the beacon, and once the packets, once the host will send the packets to the station, if there are packets from the host, if there are no packets, then it will again, if there are no packets, it will be again in the power save mode. But if there are some packets, what it will do, it will receive or it will send data to the host, and then it will this process will continue until the module doesn't have any packets. So once the module is in power save, first if the host wants to send some data, the module will check whether it's a DTM time or not. If it is not DTM time, then module again will go back to sleep. If it is a DTM time, and the module will wait for its nearest beacon and gets the data, and it will send or receive the packets that it has to the remote server. Till that process, the packets complete on its side, it will send that packet, and if there are no packets to transmit, then it will again go back into the power save mode 1. Okay, so now we will see in this scenario how much power is consumed in this scenario. So here is the graph which will tell us about how much power is consumed with the power save mode 1. So the power consumed here is around 9.3 milliamp. The higher, you can see the higher current here because it has no, there are no handshake mechanisms between station and the access point. There is no mutual agreement between the client and the access point. So the module will wake up at every DTM beacon, and it will try to check if there are any packets for me or not, and then it will go back to sleep again. So because of that, the power consumption is slightly higher here. So now we will see power save mode 2. So this is the second mode with which we will use in our modules to save the power. So this is, as I mentioned previously, this is the GPIO-based handshake, and this power save mechanism or this mode will be used when the module is in the connected state. So when station is connected to the access point, it will be in the connected state. So the commands has to be given after the module connects to the access point. So in this case, the module is already in the power save mode 2. We kept it using the command, and the module will wake up at every DTM listen interval, DTM or listen interval, and try to send or receive the packets to the peer. If there are no packets, then it will again go back to the sleep. And if there is any packet, then what the host will do is, host will assert. So here, as I mentioned previously, GPIO handshake will use 2 GPIOs. So host will use one particular GPIO to assert the module that I have some packets for you. Then module so this is basically called as a wake up request to the client. So after the wake up request is sent to the module, so module will also assert one GPIO saying that wake up indication. So I'm wake up, I'm already woken up, so you can now send the packets to me. So the station should not send any the host should not send any packets unless it receives a wake up indication from the module, from the client. So
I'm a bit confused by host. What is host here?
Host here can be a STM32, EFM32, expressive, or something like that.
MCU which is connected.
Connected to the right. It's connected to the wireless module.
Splitting the wireless processor from MCU.
And
So MCU processes sensor data. The MCU processes sensor data. And he's talking about the wireless processor.
Okay.
So how you handle the sensor data is a different problem.
Essentially two chip. One is a sensor MCU and then other is
There is two chip or same chip. Conceptually, they are different.
Okay.
Right. So so now if there is any packet from the module, then what module will do? It will send that packet to the host, and this process will be complete. Will take place unless the module doesn't have any packets to transmit to the host. And host also checks if there is any packet from the host to the module or not. If there are any packets at the host destined for the client or the station, then it will send all those packets to the module. And this process will take place unless there are no packets at the host. And if there are no packets at the module and also no packets at the host, then what will happen is the host gives the sleep permission to the host that you, okay, now there are no packets at my end, so you can go to sleep now. And this will be also acknowledged by the client saying that sleep confirmation that, okay, you told me to sleep, okay, I will sleep, like that. So if there are no packets from the host and no packets from the module, then the module goes into the sleep. But it will process, it will follow the same process. So here it asserted that GPIO and it will deassert that particular GPIO. Similarly, the module will deassert that GPIO and again go back to the same power cell mode. So this is the quick overview of how the power cell mode 2 works. So now we'll see how much.
The power cell mode 2, a few GPIO can be used, right? Not
Right.
any GPIO on the chip.
Sorry.
A few GPIOs are supported.
Right.
Essentially, you have two IO group, correct? One IO group is always alive, another IO group you can be shutting down.
Right.
You must be doing.
Right. So here in this, we will use two GPIOs. So in order to put the device in power cell mode 2, the MCU should have two empty GPIOs available so that we can use that GPIO, one to assert and one to deassert. In other words, one to wake up the module and the other one is that module will say that, okay, I have already woken up. Like
it can be any GPIO, right?
Any GPIO.
I have one question.
Sure.
So in question 2, so what is the buffer time from getting the indication to sending the data? Do we have any time allocated that we should have to send with the time?
So we don't have like that, but whatever when the AP has or buffer packets for that particular client. So when it is a DTIM beacon, so module will wake up at every DTIM beacon, and after when the beacon is a DTIM beacon, AP will transmit all the data to that particular client.
No, it's about first get the indication, right? Receive data for me. Suppose you is to transmit or receive.
Right.
So that comes after some particular millisecond or
timeout. Yes. Yes. That is a configurable timeout between that is completely specific to the vendor. So it will be in the order of
range. What the range?
It will be in a few milliseconds. I don't have the exact number, but yeah.
Put things in the context. So right now, what Joseph is saying is that we have conceptually two devices. Let us say one MCU is processing sensor data, the other device processing the wireless transmission. Now, if a sensor has an emergency, like an asynchronous input, and it has to be transmitted immediately, that MCU then wakes up the wireless device. And then the wireless device need not wait for any beacon or anything. It can instantly wake up, inform the access point it's awake, and send the data. So it can be asynchronous also. Receiving cannot be asynchronous because if somebody else wants to send you data, it comes to that access point. Access point sees that the device, wireless device, appears to be in sleep state as announced by it. And then it just queues the packet and marks it in the detail. Then the device, whenever it wakes up, has to retrieve the data. But a transmission can happen anytime. But your choice. I mean, if you feel that your sensor data is not important, you may be sampling your sensor every, say, half a second. But you may choose to send it once in 10 seconds. The last 20 collection of data, it's up to you.
Okay, do we have any error recovery at the UV side? If it is failed to get, means what is the error recovery algo? Are you using error recovery to?
We'll have that. We'll have that timeout configured in the station.
No, if the device, the form is unable to wake up at the particular time t, where the paging will right, that the quota will come. It is unable to get it. So after how much time it trying to get the error recovery done and trying to.
So that data is lost, and the station has to wake up for the next beacon, next DTM beacon.
Suppose for
it has to wait for that
3-4 becomes it unable to get it.
Right.
So is there any mechanism to recover that?
Packet will be dropped because in the buffer we cannot hold that much time.
It will drop it after a particular limit.
No,
So that-
in terms of device side, how it will recover that? It will recover with a reset, recover with kind of some algo that it will increase the clock and trying to wake up.
No, that packet is lost. So
From the device side, is there any recovery mechanism?
I think your question is whether if the receiver, when the wireless device wakes up and finds that bus has gone, train has gone, now it cannot catch the train. Now, is there a way for it to correct itself? Yes.
Yeah.
It will see that it has missed. It will stay awake until the next beacon. It will receive that traffic, the time sync signal, and then it will reset its timer, and if necessary, recalibrate.
But his question is,
Power
what
consumption
happened to
is-
that packet?
Yeah, so that entirely depends on the router. The router may keep your packet indefinitely if it has sufficient memory. Or if it is starting to run out of memory, it can discard the oldest.
Yeah.
Okay, so there's no guarantee there.
That's what the device will be.
But it might be there for you even after half an hour.
So in that case, the power consumption is more, and the packets are lost. So in power save mode 2, we have the power that is consumed is 93 microamps. So it is very less. This is because of the host and the station has a mutual contract between them, so that it will exchange some information, and depending on that agreement, the module will be in sleep. So now coming to the power save mode 3, here this mechanism this power save mode uses the message based handshake, and the module will be in the connected state. So this power save mode, as I mentioned, 1, 2, 3 will be in the will be given in the connected state, and the module can send the packets or the responses to host at any instance of time, and no handshake will be there in the receiver part. So here
The message is on which interface? Let's say host and the Wi-Fi chip is talking about SPI interface, or which one?
Yes, depending on what communication protocol being used, it may be SPI, SDA, USB, like that. So depending on that host communication protocol.
On what basis you decide that you will go with the GPI mode and message?
It's purely based on if the vendor or the MCU doesn't have any GPIOs, so they can use the message-based power mode. But in this mode, we'll see a little higher consumption because I have to say to that person, it has to understand and say that, okay, now I got your response. So that mutual understanding, there are some delays in this power save mode 3. And that is the GPIO. Directly it assesses and goes to this.
Reliability also less in the message mode, right?
Right. So we'll see a slightly higher power consumption, slightly higher. Theoretically, there shouldn't be any change in the power consumption, but due to these delays, we have little in the order of microamps. Yeah. So once the module is in the power save mode 3, we will give the commands. So these are all configurable by the commands from the host. So if first the module will check if it's a DTM time or not. If it is not DTM time, it will continue to be in the sleep. And if it is a DTM time, then module sends something called a wake up message. So okay, I have some packets, so you need to wake up and receive the packets. So what station will do? This will also check if there is any packet from the host. if there are any packets from the host, it will from the module, the host sends a packet to the module, and this process will repeat unless all the packets are completed. If there is no packet from the host, then what the module will send a sleep message. So I don't have any packets, so now I can go to the sleep or not. Then the host will give an acknowledgement that okay, I don't have any packets for you. You can go to sleep now. And then the module will be waiting for the ACK from the host. If there is no ACK, that means AP has some more data to send to the client. So if there is an ACK from the host, then module confirms or thinks that okay, I don't have any packets from the host. Now I can go to the power save mode. Go to the power save mode 8. So this is about the power save mode 3. Now we'll see the power consumption. So as you can see in the power save mode 2, we have 93 microamps, and in power save mode 3, we have around 118 microamps.
This is the current 180.3 current.
Right.
What is the actual voltage? That's we can calculate the power.
Right. So generally the module operates at 2 voltages, 1.8 and 3.3. So yeah. So generally all these measurements are taken with 3.3 voltage. Now we have 2 more modes, which are power save mode 8 and power save mode 9. So these two are given in the unconnected state. So this is also a GPIO handshake. So as I mentioned, power save mode 2 and 8, these two are GPIO based, and 3 and 9 are the message based. So this is also the same like power save mode 2, but it is in the unconnected state. For example, I have disconnected, my module got disconnected from the access point. Then also we should save some power, right? Otherwise, the module will keep trying to connect to the AP and more power gets consumed. So in that case also, we will save the power by entering or keeping the module into the deep sleep. So this is that particular mode. So this is a GPIO based handshake, and module is not in the connected state. In this case, RF and SOC will be in a complete power save. So the module will check if there is any command from the host. If there are no commands from the host, it will continue to be in the sleep after the power save command is given. If there is any command from the host, then the host will assert a particular GPIO and then indicates the module that I have. There are some commands, and module also will assert one GPIO, that is the wake up indication to host. This is the wake up request, and this is the wake up indication to the host. And the module takes the command from the host. After all the, if there are no commands from the host, then module will give the sleep confirmation. Actually, the sleep host will give the sleep request, and module will give the sleep confirmation that there are no commands to be taken, and the module will again go back to the power save mode 8.
It's a bit unrelated, but like when you're sending these commands, is there like a time delay or like time interval you keep in mind, or it's like just instant? There has to be some time interval, right?
Time interval in the sense giving the command to the module.
Module is reacting to that. How much is the time interval?
There is no such time interval, but the commands are instant. Whenever the module, whenever the command is given from the host, that delay, whatever the path from host to the module, only that particular time will be there. There is no.
What if a module is not reacting? Will you wait for some time, or a delay? How do you take into account that part?
Right. So, if, for example, if we have given a command and there is error, the module is not accepting or something like that, then it has to reset the module again, power on, and then start again. Yeah.
So when you are saying that device will sleep, so is it disabling the inputs or disconnecting the power?
It is only the connection will be same. In case of connected, the connection will be there, but it is disabling some inputs. Yeah.
Okay, so that means this is only dynamic power saving, not static power saving.
Once your host give the confirmation that the device can go to sleep, right? After that, it waits for the confirmation from host from the device, or if any new request come in between, then what it will do? It will bail out and come back, or it will complete the sleep and.
Right. So once host gives the sleep request to the module, and module says that sleep. So there are no packets from the host like that. Host will say, and station will acknowledge that by giving the sleep confirmation. After the sleep confirmation is acknowledgement given, the module will not accept any other.
But before once host give the sleep means confirmation, or give the device to sleep, but after that immediately they get the new package. They want to send the package. Then until the device doesn't go to sleep, it will wait for the confirmation, or it will again send the request.
Right. So the module, once it sends the sleep confirmation to the host, module will go into the sleep, and the packets are buffered, or the host will have some buffer, and the packets will be there. And once again it wakes at the DTM beacon, then the packets will be transmitted with some delay.
Yeah, excuse me.
So
So in these different modes, what we are seeing is that power saving basically we are trying to track. So my question is, can you go back to another slide where we have the waveform? So here we are a waveform. Yeah. So basically our focus to save power will be the peak power or the average across the whole duration. I mean, what should be the focus for power saving?
Right. So it will be the average power because once the module reset and it starts scanning for the access point. For example, if we turn on our mobile, first it will scan for the list of access points that are available. During that scanning phase, the power consumption will be very high, in the order of around 300 milliamps.
Okay, so peak doesn't matter much.
Sorry?
Peak doesn't matter.
Right, peak doesn't matter. So it will be the average power consumption, which when we say the power consumption, it is in terms of average power consumption. So in power save mode 8, this is in the non-connected state, we will have 24.22 microamps is the current that is observed. And we have, this is similar to the power save mode 3, which is host-based, message-based handshake, and this is in the non-connected state. Here, the both RF and the SOC will be in the complete power save mode. So once the module goes to power save mode, module wakes up at the configure time of 3 seconds. So this is configurable, and also this can be configurable on the host side. If there is no option at the host, then we will use this default 3 seconds to wake up and check if there are any commands from the host or not. So if there is a command from the host, then host send that particular command to the module, and this process will repeat unless until no commands are there. If there is no command from the host, then module sends a sleep message to the host, and it will wait again. This is the same process. So it will wait for the ACK from the host. Once it receives, it go back to the power save mode. If it doesn't get any ACK, so it will wait for the commands receiving from the host. So in this power mode 9, we'll have around 45.38 microamps. So this is the average power, that is average current that is drawn during this mode. So this has some limitations. I can say it's not limitations, but it has some conditions applied. So the current consumption values depend on the various factors like access point, the DTIM that is configured. Some access points will configure DTIM 1, which they wanted to send data or receive data very instantly. Some APIs will be configuring 3 or 10 like that. And it also depends on the distance between the 916 and the access point, and the environment, whether there is traffic or there is ideal environment. So these all things, the power consumption will depend. So now we will quickly see some of the case studies.
During the sleep mode, only dynamic power consumption is reduced, or static power also reduced? Both, yeah, only dynamic.
So when you say dynamic, what do you mean?
Dynamic, yeah, it's mean you just give the sub signal, some frequency with that, and the static means on device is still on condition, like voltage and.
So in this, once the module goes into power slave power save, it will wait for the indication of the host, or in according to the mode, it will wake up on its own for every dating beacon, or it will wait for the signal to the from the host to wake up. So once it gets the wake up request from the host, then only the module will wake up, and until then the module will be in the sleep.
Joseph, so Venkatesh is talking about the RAM retention case.
Right.
So is there any typical number for non-RAM retention?
I don't have that top of my head, but we do have with RAM retention and without RAM retention in ULT. I don't have the exact number. So now we'll go through some of the case studies of how the customers have implemented their product, so that the battery life. So our main focus and interest is more on the extending the battery life, right? So every IoT product should have more battery life, so that the consumers or whoever is using it, they will be benefited out of it. They doesn't need to charge very often. So
What's missing? For the recording on Zoom. So you have to make the wire wireless in Zoom, or wire in Zoom, so that you can tell you.
Yeah. Yeah.
It's your laptop to get. It's okay. See what the contents of this slide has been. Information missing.
So now we'll talk about a customer who have designed their smartwatch. So most of us are having a smartwatch. Maybe we will charge it regularly, right? So I also have my smartwatch. I used to charge it for 1 to 2 days. But the expectation here is we have to extend the battery life, so that I don't need to charge my watch very frequently. So this customer, let us look at this customer. So this customer is a leader in this wearable market, and he uses different applications on his. There are some mobile applications that he will use, and also there are some custom applications on the computer to provision the device, and then to for his application. So he has a lot of challenges. So one of the main challenge here is the longer battery life. So you can see that in the requirements. So he was expecting that the battery life should be more when a single charge with a single charge. And here he's also expecting a lot of other features, but I'm not going to focus on more on that, because our intention is more on the low power. So here the Silicon Labs comes with a extraordinary solution with which the power consumption can be reduced to a large extent, where battery life is there for around 14 to 16 days. So can you imagine, once you charge your watch, this will come for 14 to 16 days. So there are a bunch of other features, but the ultra low power, he uses the power save mode 2 and also power save mode 8 in unconnected state. So here is the block diagram. So we have this RS916 module, which is in the smartwatch. They will use a smartphone or a tablet to provision this particular device to connect to the access point and then to the cloud. And this also does the audio music streaming and also some data, using some sensors. So as you can see, once the this mobile, the provisions the device to connect to the access point and then to the cloud, it will download the streaming and some notifications and also 8DP music streaming and some peripheral and central are used to for connecting the for making these provisions and stuff. So here, as you can see, the power consumption results. So with this, he could see his watch could last for 14 to 16 days, so that the customers are very happy with whatever the longer battery life that they have. So now we'll see the smart thermostat.
What is the saving actually before you implement this power modes and after on watch?
Sorry.
How much?
It was
day of usage basically. Like
yeah, I think it was less.
Next point, you go. There in the next point. Yeah, test result is there.
Yeah, this is the test result, but what he was asking is what are the previous results without using our module. Yeah. Yeah. So thermostat. So this is also a leader in designing this thermostat. So the challenge here for all the thermostats has increased a lot in the IoT market because of the cooling and heating costs getting increased. So they have to manage that particular energy consumption. So for example, if I turn on my fan in my apartment and leave it, so power consumption is more. So due to the fact that the power is consumed when the devices are left like that without being shut down or something like that. So this thermostat will help in controlling that particular things and also reducing the temperature, giving the some configurable temperature to what I need. So it allows the user to set the particular temperature, and then this will the room will be set automatically to that particular temperature. So he also has the requirements of power consumption, and we will provide a solution with the Silicon Labs. So the power got consumed very less with that ultra low power mechanisms that we use. So here, coming to the block diagram, we have this RS916 Wi-Fi and BLE on the host, and we will use this particular smartphone to provision this particular Wi-Fi to connect to the access point and then to the cloud, and this will also be connected to the cloud. So these thermostats control and monitor at any time via mobile app and through the AWS IoT cloud. This provisioning of this thing will happen with the BLE protocol. So here the key features are of this network. Key network features are MPDT, and the power save mechanism is the key to last this battery powered device longer. Now we'll see the smart lock app use case scenario. So in this smart lock case, previously when the door is open and the module will disconnect from the AP and it consumes higher power consumption. So with this challenge, he had a requirement and the provider longer battery life of 12 months in a single charge. So we don't often charge these door locks. Like for example, if we have a traditional door locks, they are not smart locks. They doesn't need any firmware upgrade, or they doesn't need to replace the battery or something kind of that. But in case of a smart lock, it does need to have some firmware upgrade options or battery low power come into picture in terms of smart lock. So here also he uses both Wi-Fi and Bluetooth combo module, and he requires a longer battery life of 12 months on a single charge. And this with the Silicon Lab solution, we provide this ultra low power, and we will see that particular numbers here. So this is also same like the BLE. Using BLE, we will provision the module to connect to the access point and then connect to the cloud. And the main important thing is in this smart lock, there shouldn't be any disconnection. So the module has to be always connected so that the user can see and detect if there are any problems that are happening. So always on Wi-Fi with 1 second latency. For example, if I send from my from my mobile after I provision, this is also connected to the same cloud. So if I send a lock button, if I press the lock button, within 1 second, the lock has to be locked. And if I press the unlock button within a second, this is the maximum latency that is expected from the customer. So we have the test results here across. We have taken around 70 APs, and the complete door lock will have power consumption without Wi-Fi, but with Wi-Fi it is taking around 100 microamps. So this is another interesting use case scenario where mostly in the other countries we see a pet in their home, right? So they will attach this collar into the pet's neck, and they will train or restrict that particular pet to not to go into the restricted zones or out of their control. So they will use this collar in the pet's neck, and with which they will monitor here. They can also create some fencing mechanisms like geo fencing, and they can track and train that particular pet by using this application. In this scenario, the collar will be always attached to the pet's neck. So it is required that it lasts longer. They don't need to often change that particular collar, so that so for that the power consumption has to be very less, so that this collar will stay longer, or they don't need to replace every single point of time. So in this case, they will have the mobile application with which they will provision that particular this Wi-Fi and BLE to connect to the access point and then to the cloud. This will be connected using GSM, and this particular application will use something kind of a beacon with which they will measure the signal strength. They will measure the distance depending on the signal strength that is received from the beacon. So they will send some beacons, and from those beacons they will capture the RSSI of that signal, and they will measure the distance, and with that they will control that particular fences. So asset tracker is one of the most and important customer use case. So for example, in a warehouse, if we assume we have some bunch of materials that are placed in the warehouse, and if we want to search particular thing, we have to search entire warehouse, right? So these asset trackers will help in finding out that particular whatever the product, that whatever the thing that we wanted to take. So it will help so that they can find that particular thing very easily. So this particular customer uses this particular device in car. So in the other countries we have a big inventories, like they have a big, very big place where all the cars are parked. And if the dealer, this is basically a problem for the dealer, that if, for example, if I want to buy a particular car, then he has to check that particular model and where it is, he has to locate it and then get it. So if without this device, it is very tedious or very tough for him to find out that particular vehicle and then give it to the customer. So his requirement was 5-year battery life. So I don't want to replace the device until 5 years. So he will also use different key features, and he has basic challenges. One is anti-theft of the products, and also it is very complex to install. This device is very easy to install, and it is very also difficult to manage and control the vehicle theft. So for all these things, and also he had created one theft protection app with which he can locate and find out where that particular car is there. And so this is also a lot management, as I was talking. So particular car is at some place, then he will directly, with the help of this tracker, he will go to that particular location and find out that particular car very easily. So this also has a similar block diagram. This mobile application will use the provisioning, and it will Wi-Fi and BLE will be scanned. So taking the tracking uses this Wi-Fi and BLE coax capability with low power enable to scan for the BLE, and it will also check for the SSIDs which are nearby, and it will find that particular location, and the data is given to the cloud. And now coming to the standardized third-party evaluation. We have once we claim that it is our model is a low power device. So then by comparing with the other vendors, how much power can see, how efficient we are in saving the power. So this report is generated by the third-party group called Tolly. We have done with different access points and also different vendors. So as you can see here, Redpine, the modules has very less power consumption. This is in the standby associated mode. So the module connected to the access point, and it stays still. It doesn't transmit or receive any data. So these numbers are in Wi-Fi standby associated. And these are once connected, and there is some data that is going, some TLS data, which is secure, and these all measured at 3.3 volts. As you can see, there is a no co-channel traffic and 70 Mbps co-channel traffic. So here, while testing this, we have used a separate setup in an adjacent channel. So in the 2.4, we have 11 to depending on the region, we have 14 channels. So we use the co-channel traffic of 70 Mbps and measure the power consumption. So these are the low power numbers that we got. And this is in the double and BLE when it is when two protocols. So till now we have seen only one protocol. This is in the previous two slides. We see only Wi-Fi in picture, but now we have BLE also in picture. So so these power numbers are taken when the Bluetooth connection is in the advertised state and when it is in the connected state. So these are the numbers that you can see from the RS916 module. So what is the conclusion? So low power is equivalent to the longer battery life. So what I am trying to say all the way till now is, if we save the power, we will get the longer battery life. So I'll take two scenarios quickly and take you through the final conclusion. So one scenario is wearable application, and the second scenario is a smart lock application. So in the wearable application, if we consider wearable with 100 milliamp lithium-ion battery, it will consume around 297 microamps. This is without Wi-Fi, and the battery life of that particular wearable with Wi-Fi, we can see. So this is the RS916 number, 297 micro. This is the without Wi-Fi number, plus this 73 micro is the number. This is taken from the Tolly group, the table for the links is 8. So the total power consumption with Wi-Fi is around 370 microamps. So the battery life of that particular wearable is 100 milliamps divided by the total current, we will get around 270 hours, which is 11.2 days. The same is calculated with the third-party vendor, we get around 2.2 days. So that's the difference in the power consumption. And when you take the smart lock application, considering the smart lock with 4x AA cells providing 50 milliamp at the rate of 6 volts, the total power that is consumed is 34 microamps. And with Wi-Fi, this is step down to the number is step down from 6 volts to 3.3 volts because the module operates at 3.3 volts. So the power consumption without Wi-Fi is 34 plus with Wi-Fi is 24. The total power consumption is around 59 micro. And if you divide it with the this number current, we will get 2 years 11 months. And the same is calculated with the third party and the vendor, we get around 9. So this is the difference with the power save methods that we use. So this is the reference link where you can find out this information on the web. And the bottom line that I was trying to say is, in the standby associated modes, we are 25 times lower than the third-party devices, and 20 times when there is some data transfer, and 15 times greater when we use the multi-protocols. And as you can see, the projected improvement of the battery life for the smart home application is around 3 times, greater than 3 times got improved. Okay. So I will quickly explain the setup for this power consumption demo. So how we achieved, or what is the setup? So you may be curious to know what is the setup with which you are gaining, or we are measuring this particular power consumption. So this is our module EVK. This is the host that I was talking throughout the presentation. It can be EFM32, EFR32. It can be any MCU like STM32 or any other. And this is the communication protocol with which the module is connected to the host, and it has the 2 GPIOs. So I was talking about the GPIO handshake mechanisms, right? So we are using particular GPIOs here connect to the host. So we use ELP GPIO 0 and 2, and in LP mode we use ELP GPIO 6. So these are the GPIOs that are connected, and this module is connected to the access point. And here is a measurement point where we connect it to a power meter. So we can connect this to a power meter, or the Silicon Labs provides a tool where you can run the program and also measure the power consumption in the Simplicity Studio IDE itself. So if you have that, then you don't need this power meter. But in this diagram, I mentioned this standard power measurement instrument, and this particular software will be running on this particular computer. So these measurement points will capture only the power consumption, how much power that is consumed by the module. It doesn't include all these components power. It just consumes, calculates only the module's power. So here you can see a quick demo. This is the recorded demo. Yeah. So this is a Simplicity Studio tool which is provided by the Silicon Labs, where you can develop your code and flash it onto the MCU, and you can keep the module in the power save mode. So here we can configure the things, listen interval, to which access point we want to connect. All these things it can be configurable in this one, and we will compile using the same tool, and we will right now we are flashing that particular application on the MCU. So once the application code is flashed onto the MCU, we will get the console messages on this serial terminal. So as you can see, so now we are starting this energy profiler. So there is a tool with which you can measure the power consumption in the same IDE itself. So this is that particular process. So this is the energy profiler. Once you start, it will start capturing. So start energy capture. So it will start. So you have to select the board that you have connected and then click OK. Then it will start capturing the traffic, the power consumption graph. So now we will reset the module and see. Yes, so now we have reset the module. This is the firmware version. Now it got connected to the access point. The scan was success, and it gave around 11 scan results. and it connected to the AP and got the IP, and the power save command has been given. So now you can see the power got reduced to a much lower. Now I'll show you. So we will stop this recording using this button, and we can go back to the starting from the graph, and we can see that. See, from the when the module got reset, and you can see this thing, and this is the scanning phase. So it will be scanning for the access points nearby, and as you can see, the scan current, the average scan current is around 300 milliamps. So this is the scan phase, where you can see the higher peak current, but the average current will be around I think 50 milliamps. So as you can see here, the current consumption, average current consumption during the scanning phase is 50 milliamps. And now after scanning, it will connect to an access point, right? So this is that particular peak. So you can see this thing here. And after that, we will give the power save command. So now the power from here to it went into the microamps. And we can also keep the MC to a power mode. We have discussed EM0, 1, 2, 3, 4 modes, right? As Venkatesh mentioned. So that will even further reduce the power consumption to a microamps. So this is that particular current. So now we see around here 60 microamps after this connection. So this is the average current consumption. Yeah. No. Yeah, that's all.
I have a doubt.
Sure.
Actually, in this presentation, you have mentioned about the reliability and low power consumption, how efficient your device is. What about the security? And IoT are more prone to many vulnerabilities. So, any idea and solution that Silicon Labs have produced or developed regarding?
Right. So actually, the main focus here is energy consumption. So we talk more about the energy consumption. But apart from energy consumption, we have a lot of other features like security mechanisms. So Silicon Labs provide a lot of security mechanisms so that we can protect that particular device from the hacks or from vulnerabilities. So
any insight on that? How it is done? Like any technology or protocol?
That will be another 3-hour tutorial. I mean, that will be. We'll give you a lot of information. Tremendous amount of work is done in security. Hackers are there all the time. They expose vulnerabilities, and we have to make sure that that is all covered. That is a long presentation.
Sir, so in today's presentation, we got to know that in order to be more efficient, we have to reduce power. And the main gist was to understand the different power saving modes so that we can manage power. Sir, we can also do something in this circuitry, like on a circuit level, so that it should be more efficient rather than going just into the embedded part or something. So, sir, what scope we have at a circuit level that we have more efficient, like the values of inductor, capacitor, or any passive or active element? Like, what's the future scope regarding that, like in saving the power?
Yeah, like I mentioned, okay, I mean, silicon area is important. You have to reduce the number of components you're using. If you're talking about the analog subsystem or the RF subsystem, where you have inductors, capacitors, and so on, you need to have performance. See, there is a performance versus power consumption trade-off. If you don't decouple the supply sufficiently, you'll get more noise. So you have to come at that optimum point. So that one you have to iterate and figure out ways in which you can create a better circuit with less noise and so on.
So Venkatesh spoke about the power modes at the hardware level. I spoke the power modes at the software level, in the application part. So we can use both of these to reduce the power consumption further and increase the battery.
I think we're out of time. One last question here.
Last question. You have shown the power consumption in a micro watt. So the MCU fabricated by Silicon Labs, what is the vertical or structure?
We have multiple technology nodes. We have 40, we have 22 nanometer coming up. Unlike FPGAs here, it won't be like 7 or 5. IoT world is still in 22 to 40 range.
But in that, you will find a lot like
Sorry?
the structure I am talking about. Only FinFET or state all around.
No, you don't use anything advanced here. It has to be very low cost. IoT market is also extremely cost sensitive. All right, thanks everyone. My email is there, nvenkatesh@itc.org if you want to write in for anything else. And thanks so much for listening today.
To 1 minute maybe. Thanks Venkatesh and Joseph for all the talk you've given. To appreciate effort, I have a small memento to be able to them. So.
So much.
Now, so we'll have lunch break and few announcements. So lunch is being served in one place in this floor. Okay, around 24 people can sit there, and remaining people can go to the 10th floor. There are 4 rooms booked for lunches. There are people volunteering and security people. They will be guiding you there. And again, request is not to return here and there. Go to lunches. And after your lunch, you can either come back to the session if you are registered here, or you can go to respective Silicon Lab or Intel session in the other building. Okay. Thank you. Thanks for the time.